As we'll see, the session is actually a little bit broader than that. We have 5 very interesting talks. Our first talk is going to be given by Daniel. Take it away.
Thank you. Cool. So, hi everyone. I'm Daniel. I'm a PhD student. Last year, with my internship with Uber, these are the folks involved in the paper. Raj and Lazar are also here, so you can go talk to them. And yeah, so this is going to be a talk about the code transformation. So don't lose me yet. I know this is not the right session, but trust me, it's interesting. So yeah, so before I tell you about this language, I really, so this is done with Uber. I have really to tell you a bit about Uber to get you the context and the reasons that drove the design of this language in the first place. And so Uber is a pretty large software company. So it has over 4,000 engineers. And they collectively maintain roughly over 100 million lines of code. And this is spread across 7 or 8 programming languages that you can see here. Cool. And so, so as you can imagine, software development at this scale demands generally for automated code refactoring, rewriting tooling. And so what I mean by this is tools for finding finding opportunities and automating necessary large-scale changes. So to give you a very concrete example, Uber uses feature flag-driven development. So that essentially means every feature that's implemented in Uber is guarded by a flag. And so a flag is just a toggle, right, that triggers a particular behavior within Uber services. For instance, in the app, you can have this isDark mode flag that will activate dark mode. And so as time goes, and the experiments go, a lot of these flags can become stale. Right? Then what I mean here is flags that always become true or always become false. So you can think of it dark mode as permanently being on. And so if the code that's guarding this flag is not regularly cleaned, technical debt will start to build up. And what I mean here is you'll have this dynamically unreachable code, because this method is now always true. So there's a lot of clutter in the code base. And it's not only just an else block. You'll have these this import statements that if everything needs to be simplified. And this is even more challenging if you think that these changes may propagate across multiple languages and code bases. And so how can we automate this sort of cleanup task? Sorry, my mic is. I apologize. Okay. Cool. Yeah. So how can we automate this sort of cleanup task? And so we looked into multiple solutions, and most modern code transformation tools and tool sets can be placed on this plane of language specificity and expressive power. And so at one end, we have these matched replaced languages for code transformation. They're language agnostic and very easy to use, but they've very limited expressiveness power. And then on the other end, you have these very powerful compiler frameworks that allow you to rewrite and transform code using extensive APIs based on simple information and so on. But so the problem with these is that they, so the other one I told you is most of them are easy to use but limited, and the other ones are very expressive but also complex and language specific. And that's a problem, especially if you want to automate something like feature flag cleanup across multiple code bases. And so that's why we proposed this language and tool set called Polyglot Piranha, which is a lightweight polyglot code transformation language. And this language is, Polyglot Piranha is, everything in Piranha is a match replace rule. And the idea is that we extend the match replace paradigm in multiple ways to make it more expressive and usable for large scale changes. And so if you remember something from this talk, is that the idea, our core idea is that we can compose and combine multiple match replace rules in order to make them expressive. And everything in Piranha is a match replace rule. And we basically have 3 ways of composing and combining these match replace rules. And I'll go through each one of them with concrete examples. So the first one is composition within like multiple matchers with a single rule. So if you see like this code snippet here, let's say like this is just a class with like one unused private method and another used private method. And let's say like just for the sake of this example that we want to write a match replace rule for deleting unused private methods within like the Piranha language. And so what you can do is you can just like write a simple matcher using your favorite matching language of your choice. So this is using comping syntax. And the idea here is like what you see, like the colon and the brackets are basically templates. Like they can match like anything. So we're trying to match against a particular structure. So if you see here, like for this example, if you write this matcher, this is like the code you're going to select. So in this case, notice we are selecting the used and the unused private method. And like this is something you can do with other languages, not necessarily Piranha. But what's interesting now is like the goal here is like to just select and delete the unused private method. So what you can do is you can again compose and use another matcher in order to further constrain the code you're going to select. So in this case, we have like this where constraint here where they say, well, I only want to match that private method if the enclosing class, that's the enclosing clause we have there, only contains one usage of the identifier from above. So you see the name is whatever you selected in green here. And so if you notice here, this identifier, set dark mode, that we selected from there, is used 2 times within this class. So this is like heuristically, this is not an unused private method. And so like it will not be selected by Piranha because like the matchers are not satisfied. That makes sense. And so yeah, so like this is like one way in which you can combine the matchers. And then if you just want to delete the code, you can just like match this and then replace with empty string. And that's like one of the core ideas. And so like now you might be thinking that, well, this sounds very approximate and heuristic, and that's true. The transformations that we have in our language are always only going to be sound if the rules you propose are sound. Anyway, so moving on, let me show you more features about our language. And so like the second core idea that we have is the context propagation and the controlled rule application of rules within particular scopes. And so I'll show you that with an example. So let's say this is again the example from the dark mode we saw earlier. So let's say we have like this class flags, and this is dark enabled. This is just a method that's always true. Dynamically, it's always going to return true. And we want to clean this up across the code base. So what you can do, like if you just like want to find and delete this method, you can just like, look for the method that's declared with the annotation dark mode, and you can just delete it. But then if you want to propagate this across your code base, like let's say this is also being used in another class, but like in Kotlin, so you know this declaration is in Java, and the usage is in Kotlin. What you can do in Piranha is you can apply this method globally. You can say like apply another match replace rule using the context from the previous rule, but globally in this case. That means across the entire code base. So you see here like the method in the second rule is being taken, the context is being taken from the first rule that's there. And so this will be instantiated at runtime as dark enabled. And that's like what the using clause is saying there. And so if you do that, you can propagate the change again. And this will replace the usage. But then if you want to keep on cleaning up the code, you can basically add more rules in order to further clean up your code. And so what you have here, you can chain another rule call. And so you have like this, in this case, I'm saying only apply within like the surrounding code context because we don't want to do this across the entire code base. And we can have like another rule for simplifying if statements. So you can see here, if true, then you can just replace this entire statement with a consequence. So you see there, if true, we can just like replace everything with whatever is inside the true block. So everything else is deleted. And so like the idea, our idea in Piranha is that you can basically chain these match replace rules using scopes and context. So the first one is the global scope that I showed you, but you can also say, first apply the first rule within the entire code base, and then the second rule only within the context of the same file, but the first one was triggered. And you can do that within the file, class, method, and then we have like this parent scope, which basically says only apply it around the context in which the first one was applied. And you can define your own. So we support many match replace rules and scopes. Cool. And so the third way in which we can combine match replace rules is using multiple languages. So what you saw here, the syntax that I show you is just like the combi semgrep syntax, but you can also use three-seater queries and regular expressions, whatever you want. But if you want to learn more about that, you really have to read the paper, because I don't have time to tell you about it right now. Because I wanted to show you like how we use this language and how powerful it is. And so like this Polyglot Piranha toolset is deployed and used in production at Uber. And so in the paper, we basically provide 3 case studies in which we use the language to build tooling. And so the first one is automated feature flag cleanup. And then we also have 2 migration tasks that we did. And our idea with this evaluation is just like to show desirable properties of the language, like expressiveness, and effectiveness, etc. And so for this talk, I'm only going to focus on the first case study and on effectiveness and usefulness. And so in this case study, what we did, we basically built a tool based on the Polyglot Piranha toolset where, yeah, maybe that's going to work. Okay. Yeah, okay, cool. Yeah, so like we built basically a tool. I think the mic's not picking up. It's okay. Yeah, so we built a tool on top of Piranha, which does feature flag cleanup, and we did this for our 2 code bases, two of our mono repos, Android and iOS. And these are pretty large code bases, as you see here. It's like 7.5 million lines of Java plus Kotlin for Android, and 7.5 million lines of code for Swift. And we did this, like, the code is mostly open source, so if you want to learn more about how we did it, you can read the paper. But I want to tell you what exactly we did with this language. So, like, this tool, basically what it does is, like, it's a job that's running and basically produces PRs to delete flags that we think are stale. And so over the course of roughly 5 months, 6 months, Piranha produced, like, 4,700 PRs for cleanups. Like this shows you like how many of them were for Android and for iOS. And so out of these roughly 5,000, 60% of them pass continuous integration tests. And so the reason we have like this gap between, not all of them are like passing CI, is because sometimes whenever you clean up a flag, the test suite, there are semantic changes to the test suite, so like tests start failing. And like the developer has to commandeer the PR and adapt the test suite based on whatever their understanding of the flag is. And like the other big reason for the tests, for the PRs to fail CI is like it's due to linters. So basically, Uber uses a lot of linters, and like if you don't exactly follow the guidelines, the CI will not let you land your PR. And so roughly, then you can see at like 2,600 PRs passing CI. And then we also send these PRs to developers to make sure that the flag is really stale, because we don't want to delete codes that shouldn't be deleted. And so that's why we have this gap of here, like PRs that have not been accepted yet. Like developers still have to review them in order to land the changes. So like this gap is closed in the previous, like in the last months, but this is like the results we have in the paper. And so out of these PRs that have been merged, the ones, roughly 1,000 that have been merged, like the tooling was basically able to automate most of the changes. Like 90% of the changes were automated by the tool, like 90% that you can see here. And this is like the chart shows you like the total lines that were removed, and this is like ordered by this is like the ordered flags. And out of like all these PRs that were produced, like 76% did not require any user intervention. So that means like the change was just like accepted and the flag was cleaned up. And this distribution is very skewed, so you can see towards the end here, these are the user and the tool deleted flags. So like here you can see in some cases the developer goes and deletes a lot of files and classes. So that's why you see how many lines deleted towards the end of the distribution here. Okay, so that's pretty much all I have. So to give you an overview, it was like this polyglot transformation language. We have like a tool which is open source, so you can look at it. The paper is there. And yeah, we have also an open source package for the tool and the artifact, so go check that out if you're interested. Thanks.
We have time for a few questions.
Hi, the tool looks very exciting. I had a question regarding the rules. Can we specify data flow rules as well, or is it only kind of syntactic, hey, if this is found, do this is found, do this?
Yeah, so like this version of the tool, this is all syntax driven. So like the rules are only matching and replacing code.
So, okay.
So it's always syntax. You just like match and replace, but you can.
And can the rule specify context? Can I say, if find this function name and in that function something should be there?
So you can say find that function name, and then within that function you can do something.
Can I use the same function name within the function? So here, let me beat around the bush. Let me ask the question straight. So if I have if I want to remove a recursive call, how will I remove it?
I see. Like that's. Oh, you mean like deleting an recursive function?
Yeah, I mean, see, you had a rule that said if it occurs in the class only once, but the recursive call maybe the same function is called directly or indirectly.
So like this is all an approximation. So you cannot specify that.
Oh, you cannot specify such.
No, because this is it's all about matching code. So like everything is a syntax matcher. And so like some things you cannot express because we don't understand semantics at all within the language. We're just like looking at the syntax. Yeah.
Okay, thanks.
So like that's not something you can do, at least for now.
So kind of a follow-up on that question. So for those cleanup rules that are like, syntactic approximations that you can clean up, who's writing these rules? Is it driven by developers or is it mostly people that work on Polyglot Piranha?
So like the rules for simplifying expressions, like the if cleanup that I showed are already written, like someone wrote them, and like that's provided within the core of the tool. Like someone has to write them, but generally only once. Now, if you want to do something very specific, like doing API migration, which is something you can do with the language, you still have to write them manually. Like someone has to write them. Yeah.
Thanks.
I would go through the paper and look at examples of multiple languages, but could you tell me if the code is, if it is calling a piece of code in another, so do you have interprocedural rule matching specifiable where I call code in a different language?
So you can, since everything is syntax driven, you can basically apply rules across languages. So you can pretty much propagate the context of the previous rule that was like called, like say in Java to Kotlin.
Okay.
So like, since that's the reason we did it in a syntactic way, because we wanted to be able to support many languages and allow them to interleave and propagate.
Okay, so the context would be basically dependent on the rule that you specify.
Yeah, the rule gives you the context.
Let's thank the speaker again. Right, our next talk is going to be given by Mikalas, and he's going to be talking about combining symmetry and partial order reduction.
Can you say something to test the mic?
Right, testing. Okay, so thanks everyone for joining. This talk is about verification of concurrent programs and more specifically about verification by means of stateless model checking. So stateless model checking is a form of bounded verification where if we want to verify a concurrent program, we enumerate all of its interleavings one by one, and then we check that some safety property that we care about holds it each interleaving. Now, of course, this does not scale. So there have been two major approaches proposed to tackle this state space explosion problem. One of them is partial reduction, and the other one is symmetry reduction. So symmetry reduction says you can avoid ordering threads that are symmetric, that are running the same code. And partial reduction says that you can avoid ordering independent actions. So let's see what these techniques will do with a couple of examples. So in this program here, we have x initially being 0, and then we have n threads, each one doing an atomic increment on x. If we try to verify this with stateless model checking, then we'll enumerate n factorial executions, right? N threads and instructions, so n factorial permutations. And in this case, if we apply partial reduction on top of stateless model checking, we actually get no reduction. And the reason is that all of these instructions are conflicting. They are all writing x, so partial reduction considers them conflicting, and we'll explore still n factorial inner leavings. If we do symmetry reduction, on the other hand, we'll just explore one inner leaving, and the idea is that the threads are running exactly the same code. The result is going to be the same no matter what. We just explore one and we're done. In this example, we have n variables. Different variable is initially 0, and each thread is writing a different variable. Again, stateless model checking, n factorial. In this case, though, partial reduction can verify this program by exploring a single execution. And the idea is that each thread writes a different variable, right? So no matter which interleaving I pick among these n factorial, the end result is going to be the same. Each of these variables has the same value. And for symmetry reduction, again, here we get no reduction because these threads are not symmetric. So these techniques are somewhat similar. One way to view both of them is by the equivalence partitioning that they induce on the interleaving. So they effectively partition the interleavings into equivalence classes and then try to explore one interleaving per equivalence class. But so far, these techniques were incompatible. So we couldn't get the strength from both techniques into one. Now, you might be thinking, well, why do you care? If a program is symmetric, if all the threads are running the same code, can you just do symmetry reduction? And another point that I want to make is that actually either technique is inadequate. And I have a different example there, which is essentially somewhat the combination of the previous two. So each thread does a fetch and add in the beginning, and then from the index it writes this value to from the value it reads for x it writes it to an index in the array A. Now what's interesting about this program in some sense is that each thread is going to read a different value for I because these are atomic increments. So in fact, when these threads manipulate the array A, each thread is going to manipulate a different index, right? So if we look at the numbers there, ignoring the stateless model checking, partial reduction can verify this with n factorial interleavings. Why? Because there are n fetch and adds, so n factorial ways to order the fetch and adds, which are conflicting for partial reduction. But then partial reduction is smart enough to understand that these writes to A are all in different locations, so it doesn't have to order them. But in this case, if we try to do symmetry reduction sees that these are threads that are running the same code. And in fact, it will just order the fetch and add instructions in one way, say left to right. But at that point, symmetry breaks because each thread read a different value, so the local state is different. So from that point onwards, in this context of stateless model checking, symmetry reduction is of no use, and it will enumerate not only the orderings among the accesses to A, but also the orderings among the accesses to A and the fetch and adds. So in fact, the number that we get there is a double factorial of odd numbers, which is even larger than what partial reduction alone will enumerate. Right, so my point here is that symmetry reduction does not subsume partial reduction, even if the program under test is symmetric. And this is where this talk comes into play. I'll talk to you about Spore, which is a combination of POR and SR, and for this example, it can verify it by exploring a single interleaving. So Spore is the first combination of symmetry and partial reduction. It is sound, complete, and optimal, meaning no false positives. It explores the full state space of the program, and it does no redundant work. It is parametric in the choice of the memory model. I'll be talking about sequential consistency and interleavings, but these results carry over to weak memory as well. It leverages internal symmetries, which is a novel notion that we introduced in this paper, and I'll discuss in a bit. And of course, it's faster than the state of the art if the programs have some sort of a symmetry. So let me tell you how Spore combines symmetry reduction and partial reduction. So the way we do this is by adding symmetry reduction on top of partial reduction, and in fact on top of a partial reduction algorithm called trust. What's the key idea in trust? The key idea is that these equivalence classes that the interleavings of a program create can be represented as execution graphs. So if we want to verify a program, explore one interleaving from each equivalence class, so to speak, we can just enumerate these graphs. And I have an example here. So x is initially 0, 3 threads manipulate x. This program has 6 interleavings. 4 equivalence classes represented by 4 graphs, which are these 4. So in these graphs, the nodes correspond to instructions. This init node here corresponds to the initializing write to x. So yeah, this is write x, read x, and so on. The black edges denote program order. They connect the initializing write to the first event of each thread. And what's more interesting are the green edges, which show where the reads are reading from. Right? So for example, there, these reads are reading 0, 0, 0. Here is 0 and 1, and so on. Right? So trust would verify this program by enumerating these 4 graphs. Now Spore also leverages this idea of graphs. And in fact, what we observe is that actually these graphs are a very nice way to identify symmetries. Right? So for example, here, thread 2 and thread 3 are running the same code, right? They are symmetric. And we can see that on the execution graphs. So these 2 graphs can be obtained one from the other just by swapping threads 2 and thread 3. And so what Spore says is that for these graphs that are symmetric, you can identify one of them as a representative one, and then only generate representative graphs. Right? Now, so for the full graphs that correspond to a given program, for the ones that are symmetric, we pick representatives, we enumerate these ones. Now, this is easier said than done. So it's quite complicated to actually get all the completeness and optimality guarantees, but I don't have the time to go into details. If you're interested in that, please read our paper. Now, the second thing I'd like to talk a bit about is internal symmetries, because this is introduced in this paper. And I'll explain what this is with an example. The example is a Michael Scott queue. This is a lock-free queue implementation. I have the code for enqueuing an item there. I'll go over it in a second. Essentially, this queue is represented by a pair of head and tail. Items are enqueued at the back, at the tail, and dequeued from the front. So now suppose we have one thread that wants to enqueue an item. So it will start executing enqueue. It will allocate some memory, set some value to the new node, and set the next pointer. So essentially, this is what these first 3 lines are doing. And then it will enter this, this do-while loop, which is the main enqueuing loop. In the beginning, it reads tail. It reads the next pointer of tail, and then it reads tail again. This is because it wants to read tail and next in one atomic step without tail changing in the meantime. So it effectively will read these 2 pointers there, these 2. It will check if next is null. If next is null, it can proceed with enqueuing the item. In this case, it's null. So it will try to do this compare and swap. So if next hasn't changed in the meantime, it will try to enqueue the new node. So this is, let's assume it succeeds. And then finally, what happens there is that T1 notices that tail is now lagging, right? It's not pointing to the actual tail anymore. So it will try to advance the tail. But now suppose that before it does this, a new thread comes along and tries to do the same thing. So it allocate some memory for a new node. It will check tail and next. It will read the same values for tail and next, right? Nothing has changed. But then when it checks if next is null, next is not null at this point. And so what T2 is going to try and do now is it's going to try and help T1. It sees that some other thread hasn't finished with its enqueue, so it's going to try and help it. And now this is a bit problematic in terms of verification because we have contention. And so this contention on tail hinders verification. Right? And you can take my word for it, then if we have k threads, this will create a k factorial overhead. Now the key observation that Spore does, and that's behind internal symmetries, is that these conflicting operations on tail are identical, meaning that they are actually trying to do the exact same operation, but they're also idempotent in the sense that we have no way of knowing which of the two operations succeeds, right? There's no control flow in the cache. We cannot know which thread succeeded. And so this is what Spore leverages. And it says that it leverages by splitting these operations into a main one and some helping ones, which is done by annotating the input program. And then it tries to only explore executions where the main one succeeds. So all the helping operations are effectively treated as no wops. Right? And this gives an exponential reduction. Is this sound? In general, no, and I have an example on when it is not sound to do this. So in this program, x and y are initially 0, and we've erroneously annotated. So these two caches write the same value and so on. We've erroneously annotated this one as main and this one as helping. Now, if T3 only reads from the main one, then it will miss the bug. The idea is that if this read of x reads from there, then when T3 reads from y, it will see this write to y there because of the synchronization induced by the cache. But if we were to explore the execution where the read of x reads from there, then the read of y can read 0 and we would find the assertion violation. Right? So in general, this is not sound. But Spore presents sufficient conditions for leveraging these operations and for identifying when this is sound. And something that I haven't said, so main and helping do not just have to be caches, they can be functions, as long as they satisfy these conditions that Spore imposes. So essentially, you don't want to be able to distinguish which one is the one that succeeded based on synchronization, based on control flow, and so on. So this is a form where we can distinguish which one succeeded based on the induced synchronization. However, as long as these conditions apply and then internal symmetries can be leveraged, then they can also be leveraged in non-symmetric programs. So the threads that are annotated, the operations that are annotated as main and helping do not need to live in symmetric threads. They can be in threads that are not symmetric. Okay, and just a bit of evaluation. So essentially what we wanted to show is that Spore scales well enough to verify realistic implementations, and we got some real-world data structures, also some data structure from some widely used concurrent libraries, and we wanted to see how well Spore scales. We tried various configurations. So x-axis is number of threads, y-axis is number of executions, logarithmic. And the takeaway is that, of course, Spore scales better than plain DPOR, say, or plain SR. Stateless model checking, I think, doesn't appear. It just times out for most of these cases. And of course, having both internal symmetries and symmetry reductions is better than just having one of them. We have various configurations. And that's all I had. So Spore is the first combination of symmetry and partial reduction. It's sound complete and optimal, and it leverages this novel notion of internal symmetries that we have in the paper. This is the end of my talk. I'm happy to take your questions.
We have time for a few questions. So I have one question. So where do you go from here? So what's the sort of directions that this sort of leads you to? New directions?
So one direction that I think is interesting is to try and relax the conditions that we have on internal symmetry. So in principle, it's not very clear how generic these main and helping functions that we have are. Now we have some restrictions. Essentially what we say now is that these idempotent operations are a series of reads that are followed by a cas. But perhaps we could allow more expressiveness in these functions. We could allow some form of writes or in general relax these conditions and see if we can that way capture more patterns that appear in concurrent programs that we're not able to capture now. Right. And then of course there are we could also try and see if there are similar symmetries in different classes of programs, say persistency programs or some other class that we could leverage.
Just as a follow-on, can you just sort of briefly give some intuition on what the interesting challenges are with the memory model issues? How does that sort of change the kind of reasoning that you have to do in order to be able to keep soundness and optimality?
It's a bit tricky.
Okay.
So some of the completeness issues are not even related to the memory model. One way to summarize the problem is that DPOR needs to pass through certain configurations to generate some others. It's some sort of a DFS exploration. When you try to add symmetry reduction on top of that, some of the configurations that DPOR wants to go through, you might want to drop because they are non-symmetric, they are non-representative executions according to the notion of representative that you have. So what you want to do is have a notion of representative executions that DPOR will respect and that will pass through so that you're able to generate all of them.
Understood. Thank you.
Thanks.
If there are no other questions, let's thank Nicholas. Oh, sorry. Oh, please come to the mic.
Excuse me. So I mean, there are some works that they use commutations of
right.
They try to prove that some operations commute and so on.
Right.
And this can be applied, to programs with complex data structures and so on. I mean, as far as you have, if you have, let's say, decision procedure for deciding this commutativity, this can be. So how this is, I mean, can be compared with what you are trying to do, or whether they are complementary, or how they.
I think it's complementary in the sense that I suspect that commutativity conditions, you can have them, you can have them dynamically, even if the threads are not symmetric and so on, you can have some commutativity conditions. But then how it compares in terms of reduction, I don't have an answer, but it's definitely interesting to see if you can,
Because I think these examples, I'm not sure, but maybe their techniques for proving commutativity can show that this program can be turned to a sequential program or something like that, or maybe not.
I don't think you can do this for the. Okay, I'm not sure actually. I don't know if you can do this for any of the programs that we've considered, but in my head it's different. It's very interesting to see if you can somehow combine commutativity conditions with these kind of partial reduction algorithms. It's an interesting thing.
If there are no other questions, let's thank Nicholas again.
Thank you for the introduction. So this work is led by Chujun Gong, a PhD student at Ohio State. Unfortunately, he couldn't be here due to visa issues. So IsoPredict is the first dynamic predictive analysis for detecting weak isolation bugs in data store applications. Let me say what I mean by data store applications. Or first, the motivation for the work is the data store applications are the foundation of today's service infrastructure due to their scalability, a few notes, I'm just remembering, fault tolerance and ease of use. And so let me tell you a little bit about what we're envisioning here with sort of what we mean when we say data store applications. So data store application would consist of clients sending queries to a data store. This would generally be concurrent, and results would come back. So this could be like a traditional database with SQL queries. It could be a key value store and a key value distributed data store with key value queries. And results could be rows and columns or individual results. And the key point here is that these things are happening concurrently. So as an example, suppose, as a very simple example, suppose that we have an initial balance in some account of $0, and two clients are each performing operations to deposit money into that account, and one is depositing $5 and the other is depositing $3. So how would the operations look here? Well, not dealing specifically with SQL or key value, but just keeping in terms of reads and writes. To keep things general, client 1, its operations would read the value of the account into a local variable, add 5 to it, and then write that back. Client 2 would be similar, but it would add 3 using similar operations. So you can look at this probably and say, isn't there an atomicity problem here? Well, there sure is. And you can fix that with transactions, and a lot of these models provide transactions, and that's actually, we assume, a transactional model, and that programs are using transactions, issuing begin and end, or begin and commit transaction operations to the data store. So this actually, it seems like this program might work, and in an ideal world, this would actually work. An ideal world would be one in which data stores provide strong isolation or serializability, in which it's guaranteed that the execution will at least have the appearance of serial execution, in which transactions execute one after the other in isolation without interrupting each other. So one example of that would be where client 2 here, its read reads from the initial state, and then client 1 reads from the write by client 2. So they're sort of seeming to, this is serial execution. The outcome here is going to be one where the final balance is $8. However, in the real world, data stores don't provide strong isolation. They don't provide serializability. They provide weaker consistency models like causal consistency or read committed. The reason they do this is for performance reasons and scalability reasons, to get much better performance and guarantees is why they provide these. But it means that under these weak isolation models, including this example in particular here, this execution can happen under both causal consistency and read committed, which are the two isolation models we looked at in this work. If both of the reads read from the initial balance of 0, then they're both going to write 5 and 3 respectively, and the final balance is going to be $3 or $5. So that's an unserializable execution. It has a result that isn't equivalent to any serial outcome. And the problem we address in this work is that we'd like to find these unserializable executions, because programmers generally aren't intending for this to happen, and they want to know about it. But the problem is often this execution is what happens, both in testing and in deployment. So we'd like to be able to sort of look at these executions, but infer when these executions might have happened. So our problem statement, again, is to find these unserializable executions. Actually, by looking at the serializable executions is how we're going to do that. Although any mechanism would be fine for doing it. I'll show you related work now that sort of is various ways of finding these unserializable executions. This is an important problem, as others have shown, both because data stores are used so frequently and also because of this problem of unserializability violations, as many people have shown, is a really serious issue. And now I'll also try to motivate briefly that it's an unsolved problem, or not a fully solved problem. Using testing can certainly be done to try to find these outcomes. The main problem here is that you'll often get serializable executions. You won't get the unserializable executions that we're trying to detect. Classical techniques like model checking, as we just saw in the last talk, and in static analysis certainly can be effective in this area, although model checking still suffers from scalability issues, and static analysis can have many false positives. There have been techniques that are well suited for or specifically targeted toward the data store application space. One is to sort of look for patterns in dynamic executions and infer from that executions that could have had a unserializable execution, but it turns out that there still are a lot of false positives in this prior work. There's also a technique from a few years ago called MonkeyDB that what it does is that each read tries to produce a read that is legal under the weak isolation model, and it does so by choosing randomly, and it's pretty good at coming up with individual executions, or coming up with executions that turn out to be unserializable. So it does require, however, a specialized data store in order to do that. You can't run this on existing data stores. So we looked at a different direction in this work. In particular, we looked at predictive analysis. So dynamic predictive analysis, what it does is it observes a serializable execution, and just based on observing that execution, not looking at the static program at all, it predicts an unserializable execution that could have executed. So there has been prior work on doing predictive analysis for shared memory programs, both for like finding data races and also for finding atomicity violations. There are some similarities here, but there was a key technical challenge that we had to overcome, which is that conflicting accesses are only partially ordered in these weakly isolated executions. So what that means essentially is there's many possible serialization orders, or also called commit orders, that can make an execution serializable. And you sort of have to check that every single one of those is, to ensure something's unserializable, you have to check that there's no commit order that actually exists for some execution. It actually means that checking whether a single execution is serializability or serializable is actually NP hard. And that makes it even harder to do prediction. It's sort of another step there where we're also predicting over all of the possible write-read orderings. And so this was sort of intractable for doing constraint solving, which I'll talk about shortly, but we use constraint solving to solve this problem. And so what we do instead is we use an approximation that works quite well in practice, where we encode a sufficient condition for unserializability instead. So that's all I'll say about the sort of this key technical insight of the paper, because it's a 15-minute talk, but I encourage you to take a look at the details. So the basic design of IsoPredict is what I'll discuss first, and then there'll be one problem that we'll have to solve as well before the full design. So again, we assume a data store here has multiple clients issuing queries to the data store. And what we did is we added an event recorder in there in order to collect the observed execution. And in theory, you could put it sort of between the data store and the clients and not modify either one. But we actually modified the data store, in this case, a specific data store. And the reason was we wanted to know for every read what its writer operation was, because our analysis relies on that. In theory, you could design the analysis so it could sort of be flexible with respect to what the actual writer of that was, or it could determine that in some way, but we didn't deal with that challenge in this work. So the event recorder captures the observed execution. It gives that to the prediction component of IsoPredict shown here. And what the prediction component does is it generates SMT constraints that basically say three things. Based on the observed execution, it should come up with a predicted execution that is feasible, that obeys the weak isolation level, like causally consistent, and that is unserializable. The SMT solver might say no such predicted execution exists, unsatisfiable, or it might say that an unserializable execution was predicted satisfiable. In that case, it can actually report what the execution was to the programmer. So here's that specific example, again, with the deposits of $5 and $3 by the two clients, and suppose that the observed execution is one in which the actual one that we saw before, the serializable one, in which client 2 reads from the initial state and client 1 reads from client 2's write. What the predicted execution, prediction component would come up with is this predicted execution shown at the bottom. It would come up with the unserializable execution that we saw before, where they both read from the initial state. We'll report that to the programmer. So that works well enough for this example, but you might be wondering, do we have to worry about divergence? Do we need to worry about what if after some read, there's conditional behavior in the application that affects the rest of the application? And in fact, we do need to worry about that, and it does come up in a lot of the situations that we look at. let's modify the example slightly. So, not slightly, let's modify it in a significant way so that client 2 here withdraws $3 rather than depositing $3. So the application code then would look different. It would read the balance, and then it would check to make sure that actually the balance is sufficient. If not, it will abort, which will actually cause this entire transaction to seem to not have occurred at all. The read and write events will not appear to have executed in that case. Otherwise, it will write 3 less than the existing balance. So suppose the serializable, we get a serializable execution when we actually observe it. And here, client 1 appears to go first. And then client 2, when it does the read from client 1's write, it sees that the balance is $5, and so it doesn't abort. It goes ahead and writes the updated balance of 2. The predicted execution that the prediction component of IsoPredict would come up with, if, as I've currently described it to you, is going to be one in which it will say, oh, well, they can both clients can read from the initial state. However, that execution is actually infeasible, because if client 2 reads from the initial state, it'll read the value 0, which is less than 3, and so it will abort. And so only client 1's transaction will execute, which is actually a serializable outcome, because that's the same as the outcome as if client 2 goes and then client 1. So this would be a false positive. We fix this by adding some more stuff to IsoPredict to get the full design. So I've just moved things up here to make room for other components. So we added 2 things. One was we wanted to make it so that things that came after reads in the execution would, could be affected by that different red value, like conditionals, anything conditional on that value. And we don't know what that could be. It could be anything, so we're just conservative about that. That shouldn't be considered in the prediction. And we call those boundary constraints. We add those to the constraints. We can't still be sure, though, because of aborts could actually abort operations that have already occurred. And so to be more certain, we need to actually check that the execution can really occur. Also, this helps us sort of validate our technique's correctness, or our implementation's correctness. But the point in the design of why we want to actually try out these executions, is that an aborted transaction could mean that operations that in the past would actually not even appear in the execution, like we saw with the aborted execution. So instead of just reporting the execution, we try to so-called replay it. And we use this, we extend the recorder to actually try to replay this execution that occurred. Then we need to actually check that the resulting execution, which may still diverge, but in many cases we found, even though it diverged, it still led to an unserializable execution. So there was some change in the execution, but it wasn't large enough to affect whether it was unserializable or not. We would actually use the SMT solver to check whether the execution is serializable. And again, that's because it is an NP-hard problem to even check whether these weakly isolated executions are serializable or not. So we evaluated both the effectiveness and performance of IsoPredict. Not sure why I folded up my notes again. So we implemented IsoPredict's prediction and validation components. We actually extended the data store that was used in the MonkeyDB paper, and we also compared against their work as well. The methodology was that we used several OLTP benchmarks, and let me tell you just the takeaways of the evaluation in the interest of time. So for effectiveness, IsoPredict and MonkeyDB were comparably effective. Actually, they were both very effective on these applications at exposing these behaviors under causally committed and causally consistent and read committed. It'd be interesting to see what the outcomes were for programs where under these isolation levels, it was not so effective for at least one of these techniques. However, sort of qualitatively, IsoPredict is still more general than MonkeyDB because it doesn't require a specialized data store. And in future work, we'd like to explore how to actually make our technique work with any data store, sort of even in a deployed environment. For the performance, qualitatively, IsoPredict analyzes multiple executions at once, at least in essence, whereas only a single execution can be analyzed at a time by MonkeyDB. IsoPredict had long constraint generation and solving times. Actually, the constraint generation times were the longest. So that's also something to look into, largely as an implementation issue. So in summary, IsoPredict is the first predictive analysis for data store applications. In order to make this work and apply predictive analysis, we had to solve some challenges that were unique to data store applications. And as a result, there's a new way to find bugs in data store applications. Thank you.
We have time for some questions.
Hi, thank you for the talk. So you mentioned one of the challenges is sort of this exponential space of possible executions, and you're encoding these into an SMT solver. And traditionally, that's something that SMT solvers aren't very good at because you need to do some sort of symmetry breaking or partial order reduction as sort of as in the last talk. So I was wondering if you consider that, or if you do some sort of partial order reduction or symmetry breaking when you're encoding the constraints into the solver.
Right. In some sense, there's sort of two for-alls. There's the for-all over all the possible commit orders, and then there's the for-all over all the possible write-read operations. I guess what we do is we address all the possible commit orders by using the approximation that I briefly mentioned. But we address all the different write-read orders just by encoding that. And I think my understanding is that SMT solvers are potentially good at that part of it, I guess. That's sort of the magic of SMT solvers. But we are using the SMT solver as a black box.
Okay, thanks.
Very interesting talk. So fundamentally, you try to run in read committed for performance. Now you're adding the SMT solver, a validation phase, and this validation phase is very similar to optimistic concurrency control for snapshot isolation or serializability. Now the fundamental question is, are you with that approach actually faster than just running in repeatable read, snapshot isolation or serializability?
I'm not sure I understand the question.
So fundamentally, you pitch the entire work with let's run in read committed instead of higher isolation levels for performance reasons. Now you're adding the SMP solver, event recording, replay, validation. Is it actually faster than running in serializability with elaborate strategies? So Postgres would run actually optimistically things concurrently, and then also report serializability conflicts and simply abort transactions whenever those bugs are detected.
So just to be clear, I mean, the SMT solver or the validation, that's sort of all offline. We don't assume that that's sort of happening on the critical path.
So how would you, okay, thanks for the comment. So if it's not on the critical path, how would you inform an application that there was actually a bug?
So we're not informing the application live, we're just informing the developers after the fact.
Okay, excellent, thanks.
Hey, thank you for this talk. So I had this question, like, do you try to track does this analysis basically work on a binary level, or it's more of like in the source programming language that you run on top of it?
Oh yeah, good question, but actually we don't look at the program at all.
Okay.
We actually, that's one of the keys to dynamic predictive analysis is you want to avoid looking at the program and just look at the execution of it and infer as much as you can just from the dynamic execution. So we're just looking at the queries and the results of those queries.
Okay, and like something can be done in these lines, like you attach hooks to some data library which does something like with the data store and data reads. Like, does something like that also work?
I'm not sure I understand. Are you saying sort of how would you implement this?
Yeah, like instead of looking at the complete program, like add hooks to these specific calls which do something with the data.
Yes, if I understand what you're saying, like in general, you could implement an analysis like this. You just need to hook into the queries and see sort of it's just to the interface between the clients and the server data store that you need to sort of look at just that interface and see what goes across that interface, and that's the observed execution. If I understand your question.
Yeah, that's right. Okay, thank you.
Sure.
I had a quick question. So, have you thought about integrating application invariants into your model as a way of reducing constraint generation times? Because those invariants might, in fact, discard lots of constraints that you would otherwise have to consider.
Yeah, that's a good point. And also, actually, MongoDB didn't work by checking whether the execution was serializable or not. It actually checked application invariants. The one issue is that those have to be written, although they might already exist in some form. And Yeah, it's interesting to think about. Some application constraints would be difficult to encode as SMT constraints, but
I was mostly as a way of reducing your constraint generation times because they sort
Right.
of constrain the space of things that you have to look at.
that's right.
So
That's
you have
right.
to generate constraints.
As long as you can sort of evaluate those
Yeah.
symbolically or something like that, you could do that. But I mean, the written languages like Python that are difficult to analyze and so forth. So that we tried to sidestep that, but you definitely could do something like that.
Any other questions? If not, let's thank Michael again. Our next talk is remote. It's Lido, linearizable Byzantine distributed objects with refinement-based liveness proofs, and Long Fei is the speaker. So,
Hello, Long Fei. Can you hear us? Hello? Hello, Long Fei. Can you hear us? Let me try this. Long Fei?
if he's not responding, maybe we'll just we'll just switch talks. So, if Ruslan is available, we can sort of have the next speaker come.
Oh, wait. I think Long Fei is having mic issues. Now he's rejoining.
Okay.
Okay.
Ruslan, why don't we just wait? If he's available, we'll do him. Just stay up here. Just stay in front. And if we're not able to get him in the next 30 seconds, we'll move over. It looks like there's mic issues that you. I tell you what, why don't we sort of work on that offline so that we keep the schedule. Ruslan, why don't we just go ahead because we're having mic issues here. So apologies for the technical snafu, but I think just to keep things going, we'll introduce the next speaker. So our next speaker is Ruslan, who's going to be talking about a family of fast and memory-efficient lock and wait-free reclamation.
Can you just say something?
1, 2, 3. Okay. All right. I'm Ruslan Nikolai from Penn State. In my today's talk, I'm going to present a family of fast and memory-efficient lock and wait-free reclamation. This work is done jointly with Binoy Ravindran from Virginia Tech. So, non-blocking data structures is something you probably heard about, right? So they gain in more traction, more popularity because typically they provide better scalability, they provide better latency guarantees, and more stricter theoretical guarantees. With non-blocking data structures, we don't actually use mutual exclusion. So that means a concurrent thread may hold a pointer to an object which is about to be deleted. So basically, a thread holds a stale pointer. So we have to deal with this situation very carefully. And for this purpose, there is a number of algorithms exist called safe memory reclamation. And we typically use them in C and C++ code. So now with garbage collected languages, you may argue that you don't need that, but there is still, I guess, the overall problem is still relevant because even in garbage collected languages, perhaps you want to have some log-free garbage collector, weight-free garbage collector, which might be even harder. Let's take a look at the problem. Let's say thread B wants to delete an object referred by pointer P. So then we have thread A and thread C trying to dereference this pointer a bit later. Because they are concurrent threads, it's really kind of, there is no mutual exclusion, so they can still potentially access this pointer. So obviously that's going to be a problem. So now, what is the solution to this problem? Well, the solution to this problem, generally speaking, is to just postpone the allocation, to say, okay, let's delete object referred by pointer P only when it's safe to do so. But the problem with this is that we cannot really postpone the allocation indefinitely. Because if we do that, then how can we guarantee non-blocking progress? And may not be obvious immediately, but typically memory reclamation goes hand in hand with non-blocking progress guarantees. More specifically, if we postpone it indefinitely, we may run out of memory, right? So, and then can we really say that this algorithm is non-blocking? If we exhaust memory, the program crashes, so the algorithm becomes pretty much blocking, right? Even though it may not necessarily use locks. Because this definitions of non-blocking progress is much stricter than just whether I'm using mutex or whether I'm using something else, right? So by the way, regarding non-blocking progress, there are 3 types of non-blocking progress that researchers typically consider. Abstraction-free, that means algorithms guarantee that a thread makes progress in isolation. So that means if I deschedule a thread, deschedule all other threads, and this thread is running, just one thread is running, so it should be able to make progress. So obviously this is not necessarily good because such situation does not exist in practice. We always have multiple threads running simultaneously, and abstraction-free algorithms are basically prone to live locks. So this is why we have log-free algorithms. So log-free algorithms is typically something that is more used in practice. They guarantee that at least one thread makes progress in a finite number of steps, no matter what. So that means even if some thread is preempted, let's make an analogy with blocking algorithms. In a blocking algorithm, one thread that is holding a lock is preempted, then it's other threads are unable to make progress, right? So in this case, at least one thread is still able to make progress, no matter what. So obviously, this may not be enough because with log-free algorithms, we still have a problem of starvation. So we may want to have weight-free progress. So in weight-free algorithms, all threads make progress in a finite number of steps. So and obviously, weight-free algorithms are harder to design, so those are kind of crown jewel, right, of the concurrency, so to say. So another thing regarding memory reclamation is that this is what we call workload balancing. So typically, the way that it works in typical SMR, most basically threads that only make a modification will be deleting nodes, and and consequently they will be checking whether it's safe to delete this node. But this is not necessarily a good strategy, especially if you have some sort of read-dominated workload where most threads are doing some read operations, but only maybe some threads are doing write operation. So it's not completely read operations. They still have write operations. but you have only a small fraction of write operations. So in this case, we may kind of delay reclamation significantly. So by the way, this issue did not exist like with more classical approaches such as reference counting. So with reference counting, log-free reference counting, effectively an arbitrary thread would end up deleting an object, and consequently that can be a read thread or write thread. It can be any thread, right? So, but this is not the case with most SMR schemes that exist today. But why don't we use reference counting? Well, reference counting is impractical due to high overheads. For every object, we would need to have a memory. To access every object, we would need to have a memory fence. We would need to increment the counter and so on. So recent work, which was also our work, Hylene published in PLDI 2021. So in that work, the idea was to use reference counting only when effectively deleting or what we call retiring an object. So retiring means marking an object for deletion, but it's not yet fully deleted. So the idea is that with Hylene the Hylene pretty much showed a good result and relatively small overheads. But with Hylene we were able to protect against stall threads. That means threads that are preempted. They will not cause any issues. However, strictly speaking, we cannot really say that that Hylene would always use unbounded memory, right? So the reason for that is that, let's say we have a situation when some thread is iterating through some list, and another thread keeps adding new nodes to that list. So you will never be able to kind of complete this operation. So this thread is starving, so it would reserve more and more memory blocks, and eventually you can say, oh, that's unbounded memory usage. So in this work, we kind of trying to solve this problem. And we not only solve it in a sense that we are creating a fully log-free scheme like the one that will be log-free under any circumstances, but also we provide a weight-free scheme. So we have Crystalline L, which is guaranteeing log-free progress under any circumstances, Crystalline LW, which will be weight-free in some cases, but not in all cases, and Crystalline W, which is weight-free in all cases. So just to compare Crystalline with respect to other existing schemes, let's take a look at this table. So the traditional approaches, such as epoch-based reclamation, that is blocking under any circumstances. So now, if you look at hazard pointers, that's another classical approach. If we allow restarts of the operations, then we can say that this scheme is weight-free. If we don't allow restarts and just say, you have to complete an operation, the operation cannot be broken, and you cannot roll back and go back to the beginning of operation. So you are not allowed to restart it. So then it's only log-free. So now there were other recent papers, such as hazard errors, HE, on this table, which promise to have the same progress guarantees as hazard pointers. However, in our paper, we discussed that it's not quite true. And more specifically, the difference exists if you use one data structures versus multiple data structures. So the problem with multiple data structures is that if we have, from the point of view of one data structure, you may still not achieve a log-free progress or weight-free progress because no threads making progress for this particular data structure. So maybe overall in your system you're making progress, but for this particular data structure you are not making progress. So therefore, there is a distinction between one data structure versus multiple data structures. So with multiple data structures, hazard errors is going to be blocking, right? So that's the difference between hazard pointers. So hazard pointers doesn't have this issue because of some locality of the operations, so that it still checks pointers related only to this particular data structure. So therefore, it will be able to avoid this issue. But this is a very subtle distinction which was not brought into attention in the past, which we mentioned in the paper. So, Hylene from PLDI 2021 was log-free if you use it for one data structure or with restarts, right? So, but otherwise, we cannot really say whether it's log-free or wait-free because it can potentially use unbounded memory. So with Crystalline L, we can solve this problem with one data structure. So it's going to be log-free, and with restarts and without restarts, doesn't matter. So with LW, it's kind of similar to hazard errors. So we have wait-free with restarts and log-free without restarts. So now the question is, how do we solve it for multiple data structures? So now another paper, VFE, wait-free errors in PPOP 2020, extended hazard errors to make it wait-free. So all threads will collaborate with each other to guarantee wait-free progress. So in this case, we can say because all threads collaborate, so this progress guarantees will be attained even for multiple data structures. And that's the similar progress guarantee that we achieve in the most advanced scheme that we present in the paper, Crystalline W. So it's going to be wait-free under any circumstances. So just a little bit of background. Hylene, in Hylene threads, explicitly annotate each operation. So they will say, okay, this operation starts, this operation ends. Then you will wrap pointers in a special operation. And that's pretty much what it is. So when you free in an object, you're going to call a special retire call. You will not call delete or free because you cannot immediately delete this object. So the idea in Hylene 1S was to protect against stall threads. You use some birth error. So whenever you allocate an object, you would associate it with a birth error, and by using this effectively timestamp, or like maybe not precisely timestamp, but whatever the counter is, right? You will be able to protect against situations when a thread is preempted, but then you still use unbounded memory, right? So that will not happen. And that is something that we still use in our approach. So now the key difference in Crystalline L compared to Hylene 1S that was presented in the PLDI 2021 is its API, right? So its API is most similar to hazard pointers. So why is hazard pointers log-free or or wait-free, right, under some circumstances? Well, the reason why is because it guarantees that it only has a certain number of local pointers that each thread can hold. And therefore, you can always find a precise memory bound in the worst case scenario. So that means no matter what happens, whether the thread is starving, stalled, you always use a bounded number of memory objects. So effectively, in Crystalline, we modify this special operation that wraps pointers such that we would identify each local pointer by its index, and it will identify just like hazard pointers. You have indices from 0, 1, 2, 3, and so on. You will say, okay, that local pointer is 0, that local pointer is 1, and so on. So that way, protect will only reserve a bounded number of pointers for each thread. So otherwise, it's kind of similar. We have retire, marking an object for deletion. Clear will clear all previous reservations. and allocate not a special kind of wrapper for malloc where we also initialize the birth error. Okay. Well, I still have like 4 minutes, right? Okay. Oh, okay. 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 Yeah. Okay. Let me. So in Crystalline L, basically another big difference compared to Hylene is that we use dynamic batches. So effectively, we can accommodate. We don't need to accommodate for the worst case scenario how many objects we need to accumulate in a batch before we can retire. So in Crystalline L, we use the trick which allowed us to, for the algorithm to still be correct, but retire much sooner. So that's what we call dynamic batches. So now, with respect to weight-free challenges, there are two things, right? So one thing is that Protect has an unbounded loop, and the other thing is that that's kind of similar to hazard pointers or hazard errors, and that for which we use a similar approach that was used in weight-free errors. And the other problem is that retry has an unbounded loop. So basically, we had to solve that problem. So we rely on hardware instructions such as fetch and add, or double with cas, and both of these instructions allow to help to solve the weight-free consensus. So they are widely available in ARM and x86. So we don't really. I mean, although they are not available in all architectures, but at least. At least they are available in widely used architectures. So in Crystalline LW, we effectively solve the problem with retire and its unbounded loop. So in the paper, we go into more detail how we do that. With Crystalline W, we effectively had to make Protect operation bounded. I think this is one of the most difficult problems. The first problem was relatively easier with, as long as you can use hardware swap instruction. With the second problem, we had to use weight-free errors approach, and it's pretty much kind of follows the same idea. But also, it kind of diverged significantly because we only can do retirements once. We cannot go back, unlike weight-free errors. So there is a possibility if it failed, you can kind of try again and try again. Here, you have to do it in one pass, pretty much. Therefore, a number of tricks which we discuss in the paper were adopted for that. So just very quick, I'm going to show a couple of results. We evaluated scheme and compared against Hylene, hazard errors, epoch-based reclamation hazard pointers. So for read-dominated, so there is read-dominated write-intensive workloads. You can see in both cases, Crystalline performs pretty well. I mean, sometimes it can be slightly slower than Hylene because the Protect operation is more expensive. But overall, it's kind of comparable. And more importantly, like when you see like oversubscribed scenarios, like after 96 threads, it can still maintain pretty good throughput and even better than Hylene. And and this is for both Crystalline W and Crystalline L. And this is more even visible in read-dominated workloads. So now, in terms of objects, it's also kind of comparable to hazard pointers. So hazard pointers is known to be very memory efficient. With Crystalline, we were able to achieve the same pretty much efficiency. And finally, for skip list, just kind of were actually even better than all other algorithms, right? For both Crystalline L and Crystalline W. And again, in terms of memory efficiency, it was very memory efficient. Thank you so much. Code is available on my website, and I will gladly answer your questions.
I think in the interest of time, so that we stay on schedule, we'll take the questions offline and we'll move to the...
Okay.
Let me ask. Hello, Longfei. Are you there? Hello, Longfei. Are you there? Okay. Can you get your slides up? Okay. We're having some issues with your audio, but we'll tell you when to start. Okay, can you say something into the mic, Yufei?
Hello? Hello, do you hear me?
Great, yes. So I think we've resolved the technical issues. So with that, Longfei, please start your talk.
Okay. So I'm Longfei Qiu. I'm a PhD student at Yale University, and I'm presenting Lido, which is a novel model of Byzantine consensus protocols that supports proving both safety and liveness of these protocols through refinement. And this is joint work with Young-Sung Kim, Jiyoung Shin, Jun Kim of Honora, under advisor Professor Zhong Shao. So for some background of our work, I will begin from an introduction of Byzantine consensus protocols. A consensus protocol is an algorithm that makes a group of networking nodes behave as if they were a single atomic state machine. Of course, any networking system cannot be truly atomic, since you always have latency between submitting requests and receiving result. And so the correctness condition is defined by the well-known concept of linearizability, which says any network trace is linearizable to an atomic state machine. And so it's also called a state machine replication algorithm, or SMR. Now, beyond safety, of course, we also expect the protocol to satisfy liveness, which means that if a client submits a command, then it's eventually executed. And finally, we expect the protocol to tolerate a subset of Byzantine faults, meaning when the nodes are faulty, they can send out any possible message. And that contrasts with benign faults, where if the faulty nodes do nothing. So any networking system relies on message delivery to get progress. And so we need to consider different models of communication. In an asynchronous model, there's no guarantee on the front of message delivery. They can take arbitrary time to arrive. While in synchronous networks, the assumption is that there is a known bound delta or message latency. However, both these models are not very realistic. And so the most important class of protocols work under the partial synchrony assumption, which says there is a unknown time point called the GST. Before GST, there is no guarantee on the message delivery latency. But after GST, there is a known bound delta on the latency. And in this work, we mostly consider consensus protocols under the partial synchrony assumption. So in the literature, there are a very large number of consensus protocols that has been proposed, and a very large number of them work. They follow a very general paradigm called the round plus pacemaker structure. In these protocols, the protocol is structured as an infinite sequence of smaller protocols called rounds, and each node only participates in one round at a time. And if all the nodes are in the same round, and the leader of round is non-faulty, then it's guaranteed that it can make progress in the system. However, as we all know, the nodes could be faulty. And so when the leader of a round becomes faulty, there is a mechanism called the pacemaker that kicks in and moves the system to the next round. Now here is a very simple description of the pacemaker. You just observe whether there is progress in the current round. If you don't observe any progress, you broadcast a message called the timeout. And if you collect a sufficient number of timeouts, you enter the next round. It sounds very simple, right? However, it turns out this very simple implementation of the pacemaker does not satisfy liveness unless we make additional assumptions on the network. To make it actually work, you need additional tricks. And here you can see several different ways to make it actually live. And the red part shows you the difference between these versions. But you can see that they have very subtly different liveness properties, which is why these Byzantine consensus protocols are very difficult to implement correctly. Now, in the literature, there already exist many existing works that analyze the safety or liveness of these protocols. But so far, we haven't seen any general framework for proving both safety and liveness of these protocols. And this leads us to our contribution, which is called the Lido model, which we claim supports proving both safety and liveness of these protocols through refinement. So this figure shows you the structure of our safety proof, which takes the form of layered refinement. At the very top level, you can see there is the SMR interface where the clients submit requests and receive responses. At a slightly lower level, the clients send the requests to individual proposers in the system, and the proposers are coordinated by an abstract pacemaker. Roughly speaking, the proposers execute the requests by following 4 steps. First, it needs to get the consensus log, and then it appends the method to the log. And finally, it commits the changes to the log. And if all these procedures succeed, then it passes the control to the leader of the next round. Now, of course, the proposer could be faulty, and so it needs to work with a group of voters to ensure correctness. And the voters are implemented by running an infinite loop of receiving requests from the leader and checking if it's safe to vote, and if yes, then it sends the vote, otherwise it drops the request. And finally, at the lowest level, we have the network model where these proposers and voters are implemented on individual networking nodes. We also support proving liveness by refinement. We observe that in many of these SMR protocols, liveness reasoning follows also a very general pattern where the pacemaker allocates a fixed amount of time to each round. And within each round, it's divided into several events, including making the leader enter the round and then executing a number of phases. And if each phase succeeds, it's guaranteed to commit at least one method. So to summarize, our contribution is a Lido model, which is a pacemaker-aware model of partially synchronous SMR protocols. And we also obtained safety and liveness proofs for a modern Byzantine consensus protocol called Jotion, based on our Lido model. And in the following slides, I will first introduce the Lido model and then show some details of the Jotion implementation. But I will skip a lot of details due to limited time, but you can find them in our paper. So the Lido model is based upon our previous work on a model called the atomic distributed object, called ADO, where we used it to implement several benign consensus protocols and verified their safety but not liveness. The core idea of ADO is that we use a cache tree based abstraction for the consensus log, And we model the growth of the log through 3 steps, which we call pull, invoke, and push. And we represent the result through these figures called cache nodes. Now, the ADO model was successful for benign protocols, but when we apply it to the liveness of Byzantine protocols, we immediately encounter several problems. The first, of course, is that it's an atomic model, but we can't. And to say that a protocol refines the model, we reorder the network events, but in reordering events, we destroy the temporal properties. And so we reformulated ADO as a concurrent but linearizable object. The second issue, of course, is that it lacks information about the pacemaker, without which, as we have seen, we cannot do any liveness reasoning. A solution, of course, is we augment the ADO model with an abstract pacemaker state. And this leads us to the Lido model, which is summarized in this figure. On the top part, we have this. We still have the ADO cache tree, which are controlled by the pull, invoke, and push operations. In the bottom part, we have this start next and elapse operations, which represent a abstract timer. So start next represents the operation where the leader passes control to the next round. But if the leader does not cause it, then the pacemaker comes in and calls timeout start next to start the next round. So to see how this works in practice, I will show an example trace of Lido. So on the top right part, we see the pacemaker state, which consists of round and remaining time. In the bottom part, we have the cache tree, which initially contains only a single node called the root node. Now on the top left part, we see the committed consensus log, which shows how Lido refines SMR. So let's assume that GST does not occur until the third round. So in the first 2 rounds, the operations may or may not succeed. So in the first round, the leader comes in and first calls pull, which is to get the up-to-date cache log. Of course, it only obtains an empty log since there's nothing before the first round. Then it proposes its own method, let's say method A. That's the only method in the log right now. Now, it tries to commit this method A, but say due to network failure or not enough time, it fails, and this results in a T cache. So the pacemaker comes in and starts the second round. In the second round, fortunately, the leader sees the method proposed by the first leader, and so this E cache is drawn from the first M cache. Then the second leader appends its own method, let's say method B, and attempts to commit the log. Unfortunately, it fails as well, resulting in the T cache shown here. Now the third round begins. The leader sees only method A by the first leader, but not the method B. It appends its own method C, and it attempts to commit the log. This time, since it's after GST, well, it succeeds. And at this point, the method A and C are committed, so you can see it on the top left part, the committed consensus log. So this shows that Lido defines a transition system which captures both the state of the consensus log and the pacemaker. And we now look at how we can prove liveness of SMR protocols using this model. So our first observation is that in general, we only care about non-zero traces of systems, which means that in any finite period, there can be only a finite number of events. And this inspires us to represent an infinite network trace in the following way. We will just divide. We start from the GST time point and then divide the time by periods of delta. So here at GST, the trace is tau 0, and then by the time GST plus delta, we have the trace tau 1, and so on. And what this gives us is that we can easily state the liveness assumptions as safety properties on each period. For example, to represent the partial synchrony assumption, we will just say, if you send a message before the beginning of a period of delta, it's delivered at least once before the end of the period. And with this, we can summarize our liveness proof in 3 simple steps. First, we formulate a set of safety conditions on the segmented traces of Lido. Then we prove that under these conditions, we can commit new methods infinitely often. And finally, we just show that all the live network traces refine all the live traces of Lido, which implies that at network level, you also commit new methods infinitely often. So we applied our methodology to a Byzantine consensus protocol called Jotian. It's a two-phase protocol that's also being deployed in the industry. And the figure below shows how our implementation model works. It's a main process with a timer attached, and the main process has handlers for external request messages and timer signals. These handlers can then be extracted to OCaml code, which makes it an executable implementation. This figure summarizes our proof effort. So as you can see, the safety proof took only around 4,000 lines. And the liveness proof took around 1,700 lines, which shows that our methodology is a very efficient way to prove safety and liveness of SMR protocols. We also mentioned that in recent protocol design literature, there is an important optimization called pipelining. It reduces the best case latency of these protocols, but it also decreases its worst case latency. It's slightly more difficult to verify because pipelining depends on cooperation between consecutive leaders. Nevertheless, our leader model applies to these protocols as well, and we obtained safety and liveness of pipelined Jotian. So to conclude, we introduced Lido, which is a model of consensus protocols supporting both safety and liveness refinement. And we obtained, we believe it's the first mechanized safety and liveness proof for a pipelined Byzantine consensus protocol. We also mentioned that our work leaves a lot of ends open. For example, we only considered partially synchronous consensus protocols with a fixed set of participants. But in the blockchain industry, we also need other kinds of protocols, for example, asynchronous protocols or protocols that support open membership. And handling these kinds of protocols are work for the future. And again, I'm skipping a lot of details due to limited time, but you can find all those details in our technical report and artifact, which is available on our website. That's all. Thank you.
We have time for a quick. We have time for a quick question.
Yeah. Thank you for the presentation. And we'll have lunch.
Hi. 1, 2, 3. Okay.
Very nice.
I've got one here. For me.
It's there. It's muted. And which one is it? I think that's the one that's on. Pretty sure.
Test.
Yeah. And it's just and two is.
You want to put your screen into the correct mode?
Yeah.
When I introduce you, is there anything you'd like me to say? Like you not on the job market or anything like that?
Mm-hmm.
You are?
Oh, sorry.
When I introduce you, is there anything you would like me to say? Like maybe something? Is there something you would like me to say?
Yeah.
Nothing?
Yeah.
So you're a graduate student at Cornell?
Yes.
That's very nice. Plenty of figures, it's irrelevant, but it's important. It's also pretty good. Look at me. You want to I'm looking for a job. All right, it looks like it's time to start. So my name's Steve Blackburn, and I'll be chairing this session. It looks like it's going to be a really fun session. And we have our first speaker ready here. It's Hongchen Chen, and he's a graduate student at Cornell University, and he's going to talk about Allo, a programming model for composable accelerator design. Thank you.
Yeah, hi everyone. Welcome to my talk. And I am Hong Zheng, currently a third-year PhD student at Cornell, supervised by Professor Zhiru Zhang. And today I'm going to talk about our work on Allo, a programming model for composable accelerator design. And this work is in collaboration with Niansong Shaojie from Cornell and Zhichen and Mongjia from USTC, who were also interns at Cornell. So over the past 2 years, we have witnessed the size of deep learning models grow exponentially. In order to satisfy the increasing computation demands, many researchers and companies turn to specialized hardware accelerators to accelerate those applications. However, accelerator design is quite different from programming on general processors. It requires users to manually handle the custom processing engines, custom memory hierarchy, and custom data communication, which is far more complicated than general programming. The first challenge of designing high-performance accelerator is to balance manual control and compiler optimization. Here, I show a code snippet of matrix multiplication written in C++ high-level synthesis. And we can see that even with the help of HS, the code is still very complicated. Starting from a vanilla MapMal kernel, we may add compute customizations like loop tiling, loop unrolling, and pipelining, which requires manually rewriting the loops. Furthermore, we may also include custom memory hierarchy by creating intermediate buffers and conducting memory partitioning. So lots of pragmas and I/O logics will be inserted in the original code. Lastly, we may also incorporate data movement optimization. It requires programmers to restructure the code into multiple pipeline stages and connect them using FIFOs. From this example, we can see that it may take about 500 lines of HS code, even for a small systolic array. And this approach is vendor-specific, hard to maintain, and not able to reuse across different applications. Existing high-level synthesis compilers like ScaleHS attempt to tackle this problem to provide automatic design space exploration. However, since it only considers compute customizations, the overall performance is still far from the optimal manual design. Therefore, To tackle these challenges, we propose Allo, an accelerator design language and compiler. Allo is the preface of Allo solvers, meaning different kinds of hardware. We make several design principles for our programming language. The first one is Pythonic. Since nowadays Python is the most popular programming language for deep learning and data analysis, a Python embedded language is more acceptable by programmers. As shown on the right, users can firstly define an Allo kernel in Python using a basic three-level nested for loops to calculate the matrix multiplication of seed equal to A times B. We support free-form imperative programming and support Python native keywords. So users do not need to learn a new DSL, but can easily write a Python program as usual. The only difference is that users need to explicitly provide the type annotation, which will be used to infer the bit width of the actual hardware modules. On the contrary, the previous DSLs like TVM tensor expressions use a declarative way to write a program, which is not straightforward and it's hard to express control flow that is very common in hardware accelerators. To ensure productivity and maintenance of hardware designs, Allo also inherits the idea of highlight and TVM by separation of concerns. Allo does not decouple the does not only decouple the compute customizations, but also decouples memory and communication customizations from the algorithm, which enables more complicated optimizations. In the middle end, we use MLR as the intermediate representation. Different from TVM that use a monolithic lowering approach, Allo enables stepwise verified revise. So users can immediately print out the transform module after applying each primitive to inspect whether the customization is expected. In the following, I will use an example of transforming a gem kernel to syslolic array to demonstrate how to write a program in Allo. After users define an algorithm in our front-end language, we can create a schedule by calling allo.customize. A schedule here is a sequence of customization primitives. We can see from the architectural diagram on the right, the default implementation only has one PE and reads data from A and B tensors and write back to C. After creating the initial schedule, users can apply schedule primitives to customize the hardware design. For example, buffer add is to create intermediate buffers between the PE and the input arrays. And unfold can explicitly unfold the loops into multiple hardware processing engines. Partition is the memory customization that creates more memory banks along specific dimension for parallel memory access. And relay is the communication customizations that connects the buffer with PEs using FIFOs. Finally, we can achieve this output stationary syslolic array. From this process, we can see only a line of schedule code is needed, which greatly simplifies the programming burdens to construct a complicated syslolic array. To test whether the results are correct, we can lower the code to the CPU backend and leverage our LVM execution engine to run the optimized module. However, the CPU simulation cannot easily identify bugs like deadlocks in a data flow design, and we need a stronger guarantee for those customizations. Therefore, we integrate a formal equivalence checker that we propose in the PLDI'24 paper to formally verify the equivalence of the vanilla module and the transformed module. The verifier uses a symbolic execution and can quickly support statically interpretable control flow and verify large designs very quickly. After we make sure the design is correct, we can finally push the design to the HS backend to do the hardware synthesis. And we can see that Allo-generated syslolic array can achieve the same performance of the state-of-the-art syslolic array generator AutoSA, but with much lower resource usage. Moreover, our customization primitives are expressive enough to construct different data flow architecture. compared to previous approach that leveraged space-time transform to generate systolic array. Allo provides an easy way for users to quickly change the size and the configurations of this different systolic array with minimal schedule code. Now, suppose we have already optimized the single kernels. The question becomes how we can compose those kernels into a functionally correct and high-performance accelerator. Here, we showed an example of cascading two mammal kernels, which is very common in nowadays transformer-based language models. We propose a compose primitive that allows users to incorporate the previous defined schedule to the top-level function. However, simple composition is not enough. Just like playing a puzzle, not all the pieces can be matched perfectly, and we need to find the right piece and connect them together. Specifically, if the output argument of the intermediate buffer of the first kernel is partitioned along the 0 dimension, then the input of the second kernel should also be partitioned along the same dimension. Otherwise, the interface mismatch, and the kernels cannot be connected together. So the goal here is to model the function arguments in both callers and callees, and to make sure the function interface or the layouts are the same. To maintain the argument information of both callers and callees, we construct a hierarchical data flow graph, where each node contains the name of the variable and the function that the variable resides. Then, in this case, we need to guarantee the 3 nodes in the red box have the same layout. This is exactly what type checking does. Therefore, the key idea is that we can model the data layout as a type. We have 4 base types. Bottom means complete partition, top means no partition, and C alpha means cyclic partition with a factor of alpha, and B alpha means bulk partition. And then we construct a subtyping relation between these base types. Basically, we want to make sure we always provide more read or write parallelism for the variables, so the kernels can always be executed correctly. For example, if a kernel accepts an argument without memory partition, then if we provide a fully partitioned variables into it, then the kernel still can run. Therefore, we have these 2 subtyping relations. And actually, this subtyping relation forms a lattice, which provides a very good property for our inference algorithm. So the data layout propagation problem just becomes a type inference problem in this type system. To make sure the global consistency, we leverage the worklist algorithm to infer the types. Since our problem has a very good lattice structure, so the inference algorithm is very efficient and can converge in linear time. The formal proofs can be found in our supplemental material. For the experiment, we first conduct a single kernel evaluation. We take the designs from the Polybench benchmark and compare Allo with other baseline systems, including the basic Vitis HS, 3 accelerator design languages, HeteroCL, Dahlia, and Pylog. There are also 2 automatic HS compilers, Scale HS and Merlin, that leverage automated design space exploration to generate hardware designs. And we can see from this figure, Allo can always achieve the best performance in these designs with orders of magnitude better than the baselines. This is mainly because Allo has sophisticated memory and communication customizations that create efficient memory hierarchy and data placement schemes. This experiment also proves that only searching the compute customization using DSC is still far from optimal. Apart from latency, we also conduct analysis on the resource usage of those designs. Compared to the state-of-the-art HS compiler Scale HS, Allo achieved lower latency by reducing the initialization interval to 1. Since the design is better pipelined, we also achieve a higher place and route frequency. To demonstrate the scalability of Allo, we also conduct multi-kernel evaluation by constructing a complete LLM accelerator. We take the context GPT-2 model and create a fully pipeline data flow design for this model. In Allo, since we have already optimized the kernels, we can directly compose each submodule together to form a complete design. We mapped the design on an AMD U280 FPGA running at 250 MHz and evaluated the design in a single batch, low latency generated inference setting. Compared to the previous overlay design DFS, we can achieve 2.2 speed up in a preview stage. Even compared to the A100 GPU, our accelerator can still achieve a better performance and much higher energy efficiency for long output sequence. And most importantly, we can achieve this amazing performance in Allo with less than 15 lines of scheduled code. To further make our design more accessible to other researchers, we also encapsulate those neural network operators into a library and integrate Allo as a backend compiler of PyTorch 2.0. So users can directly import the PyTorch model and generate the optimized accelerator design in a push-button way. To sum up, we propose Allo, a Python-embedded accelerator design language that is able to generate a large-scale accelerator in a productive way. In the future, we will also target other backends like ASIC and MPU, and try to include more automations in Allo to further reduce the programming burdens of writing a schedule. Also, sparsity support will be incorporated in our framework in the future. Our code and artifacts are open source. Please feel free to take a look. And that's all of my talk today. Thank you, and I'm happy to take any questions.
We've got time for a question or two. Any questions? Can you please state your name and affiliation when you ask your question? Thanks.
Nice talk. I'm Sang-gyu from Seoul National University. So I guess the FPGAs have limited memory, so you'd likely have to distribute your model among different FPGAs. Do you have any support for that?
Yeah, so our group is currently working on that. So currently, for this PLDI work, we only target a single FPGA device. But actually, in our other paper that was published in FCCM'24, we discussed the possibility of scaling the accelerator to multiple FPGAs. And you can refer to our papers. And we are also working on that.
Thank you.
Hi, May Milano, Princeton University. You have a subtyping scheme where you're able to infer types.
Yeah.
Are you inferring principal types?
What do you mean by principal types?
Is there a notion of a most specific type for everything, and does your inference algorithm find that most specific type?
Yeah, so basically we try to unify the layouts. So if the memory layouts of two kernels are not the same, we try to find the least common value on the lattice and try to unify them. So you can refer to our paper for more details.
Thanks.
Okay, I think we're running right on schedule, so we might go to the next talk. So thank you, Hongjian.
Yeah, thanks.
All right, and our next speaker is Joe Raskind from SUNY Binghamton, and he's going to be talking to us about Vesta, power modeling with language runtime events. Thanks, Joe.
All right, great. All right, good afternoon, everybody. And yeah, I'm going to be talking about my paper, Vesta Power Modeling with Language Runtime Events. So first, a bit of an introduction to why power modeling in the first place. Well, with power modeling, we're interested in, energy efficiency, understanding how much power certain applications are consuming, right? So when it comes to that, right, everybody here, they have mobile devices of some sort. They've got batteries on them, and you'd like those batteries not to instantly, dissipate, right? So if we write programs that take up less power, be able to use our devices longer, that also sort of corresponds to, say, data servers, right, which are running millions or, thousands and thousands of different programs at a given moment. And if we have those programs consume less energy, then there'd be less operational cost associated with that power consumption. That then sort of goes with, more power means more heat, and therefore the more need to cool those data servers, so less power, less heat, less cooling. And also if we're concerned with energy efficiency, right, or if we're concerned with wanting to continue to use our technology stacks or whatever for a longer period of time, right, if we think about the future, we want to make sure that we can continue doing what we're doing for as long as possible, right? And if we want to be doing that, we want to reduce the amount of power that all of our devices or applications are consuming, right? So if we're then interested in energy efficiency, we're very much then going to be interested in power modeling, kind of the pillar of energy efficiency. And normally, if you're building power models, state-of-the-art gold standard is using an HPC-based power model. So what are HPCs? They're hardware performance counters, so registers on a CPU that are going to tick up, keep an accounting of any time, say, a TLB miss occurs, a cache miss occurs, a floating point operation, something to that effect, right? And normally you'd build a power model based on that. So you'd have some kind of linear model that then maps these different counters up to power consumption, right? But there's a few limitations to doing so. One of which is if you're trying to model the power for an application, right? You're violating the principle of least privilege there. You want an application power model, right? You want to know how much that application is running. You're going here, you're stepping outside of the boundaries of the application and going down into the hardware, right? And also these HPCs, they're going to get ticked up regardless of just your process, but other processes running on a given machine, okay? That also gives kind of a difficulty when wanting to explain logically what's going on with these models, right? What does it really mean if you have, say, millions of cache hits causing power, a larger power drain, when, again, multiple processes can be running at the same time, right? It's not specific to your application. So then the question is, can we do better than that, or at least, for those particular problem points? Can we build some kind of power model that uses application-specific language runtime events, okay? And of course, for Vesta, the answer to that is yes, we can do that. So Vesta provides a novel methodology that uses JVM events to build power models. So here, by using JVM events instead of HPCs, what we're doing is we're capable of satisfying the principle of least privilege because we're just inside of the application domain, right? We're not jumping down into hardware specifically. And ideally, right, all those different events that we're tracking are going to tell us something about the application itself, right? So our model is going to tell us, or at least give some kind of indication to a developer, perhaps, of saying, oh, this is why certain, I consumed more power in this instance, okay? In terms of the tool itself, Vesta is very lightweight. It's capable of, predicting energy with a mean average percent error of our 37 different benchmarks that we checked of only 1.53% error. And in the paper, we provide a study on event importance and model explainability with these JVM events. Okay. So in terms of the design of Vesta, it's pretty simple and hopefully decently intuitive here. Basically what we're doing is we have these JVM events, we have some energy, right? We have an application that we're looking at and monitoring. From that, we then create a trace using that event and energy data, right? So bucketing together all this information, building a model out of it, and then ideally having some nice accurate predictions. Now in terms of how we get that energy data, what we use, since we're JVM focused, we use a tool called JRAPL. It's kind of a wrapper around Intel RAPL, which is going to interact with that C interface to get power readings and energy readings. From that, how do we get our JVM events, or what exactly are the JVM events we're using? Well, we use these things called USDT probes, so that stands for user statically defined trace points, kind of locations inside of the hotspot OpenJDK that we were using for our testing that's going to give us indications of when certain events occur. Okay? And there's quite a lot of these events that exist in the JVM. So here is kind of a snapshot of the events that are available. So these are the 24 different probes that we monitor. And you can see that they're very diverse. They tell you a lot about the application's runtime. So method probes, JIT probes, memory management, exception handling, concurrency, a lot about how the application is running, right? So things about garbage collection, new objects being made, et cetera. However, in reality, the probes don't really look this nice from sort of the outset. Most of the probes that exist in the hotspot JVM, 94% are what we call split phase. So really, they look more like what's shown in this table, where we have events that have entry and return behavior. So we see get long field entry, get long field return. Whenever we step into getting a long field, that entry fires. When it finishes, it returns. Okay, so that's the idea, or those are the probes that are initially exposed. So the difficulty then, and what's different between HPCs is the HPCs, right? The cache misses. It's a single event that ticks the counter up. It's not quite the same thing with our language runtime events because we have normally multi-threaded processes, right? The JVM is going to spawn a bunch of different threads, and then perhaps have a lot of these events occur at the same time. So what does that really mean to have, say, 5 get long field entries and no corresponding exit? Right? So it's kind of a difficulty here. The way we solve that is through this idea of tracking these split phase events and taking note of their state and their intensity. So there's a more formal description of how this is done in the paper, but hopefully this provides kind of an intuition for it. The idea is that we have our different timestamps with all of our different events being fired. And if we see, say, like what's shown here, an entry, we're going to tick up that depth. We're going to keep doing that. So in the next timestamp, we see another entry. We're now at depth 2. In the third timestamp, we see an entry and an exit. We're going to tick up the depth, but keep note of the fact that we saw an exit, so in the next timestamp, we decrease the depth, saying, the idea here being that we're keeping track of all these different events occurring and trying to understand the state of the runtime system as it's executing, okay? So that's really what we're matching to power. So another unique challenge associated with Vesta here is the idea that we're not, unlike HPCs, which traditionally they use linear regression techniques, right? So a linear regression model, which fits quite nicely with the intuition of how these HPCs can be mapped to energy. Insofar as you have a cache, different levels of caches, TLB, an ALU, right? All these different components that when added together gives you the total power consumption of that device, right? It's not quite the same. We didn't find that to be the case with our runtime events. These JVM events, they didn't have that kind of nice additive behavior associated with them. They're very nonlinear in the way that they were structured. Okay? So at the end of the day, we had to choose a then nonlinear model in the form of a decision tree. So for Vesta, we used XGBoost, which is a gradient boosted decision tree, and it worked quite well for our data set. We also explored using linear models and neural networks, which you can find in the paper on how that went, not particularly well, as opposed to the decision tree. So for evaluation, some experimental stuff, we used 37 state-of-the-art JVM benchmarks, so 14 from Da Capo, 23 from Renaissance. More on the machine information and all that in the paper, and the default configuration for the JDK we used was OpenJDK'24, but more on that in a little bit. So the whole point is we're building a power model, right? So the theoretical stuff is nice and interesting, but does it actually work? And the answer is yes. It works pretty well for us, very well in fact. Like what was mentioned before, we have a mean average % error of all these 37 benchmarks of only 1.53%, meaning that for overall power prediction, Vesta does quite well. Okay? You also have the capability, so this is something that you could look at. All these graphs can be replicated for yourself on using the artifact that we have. You can see you could look at a per trace that here we have a black line indicating ground truth, blue line indicating the blue dashed line indicating the prediction for Vesta of those different timestamps, and that the model does a pretty good job of managing or understanding the trend of power consumption for here the Dottie benchmark, so with only an error of 0.74%. Okay. Now, what's really interesting about Vesta is the idea of explainability, right? Since now we're kind of at the application level, we can see how things about how the program was written is really going to influence power consumption. So what's shown here is a graph detailing feature importance. So what we see is a ranking from the least important to our most important features using SHAT values. So if you don't know what that is, it's a pretty popular metric for machine learning that indicates with a high average or a high absolute value that that particular feature had, for our purposes, quite an impact on the power state, on dictating to the model when the state is fluctuating in one way or the other. And what we find is that kind of intuition about certain aspects of a runtime system does, in fact, influence power consumption, like concurrency with thread park, memory-related tasks like a GC, creating new objects and setting objects. Right? So we find that those being the most important in making decisions in energy fluctuation for Vesta. We can also go and look at exactly how the different splits occur in the decision tree. So here it's a little bit cropped. In reality, you could look at a much more detailed decision tree with all the different branches. The orange highlight is showing exactly where the splits are occurring. And we can see that for this kind of arbitrary trace, we're going from one split to another to eventually get our predicted power for that interval of 56 watts. So the idea is that, if a developer is looking through this, they could have some understanding of how their application is moving from one power state to another. So I mentioned before, I made the claim that Vesta is pretty lightweight. Here we see some overhead stats. Energy, only about 2% overhead. Reference cycles, 3%, and wall clock time, a little bit less than that. So Vesta is a very lightweight tool, which does not impact too much the actual behavior of the applications we're taking a look at. So I mentioned before that we didn't just use the OpenJDK19, or at least we used that as kind of a default. We wanted to make sure that this wasn't just a fluke on our given machine, right? So we used a bunch of different configurations and combinations of things to see does Vesta work just as well. So we tried different GCs, so the default being G1 GC for JDK19. We tried the serial, parallel, ZGC, all these different JIT compilation or different JIT configurations, a different JDK, so going from 19 to 11, that worked just fine, and also trying out Vesta on different machines, right? So still Intel CPU since we're using RAPL, but a different CPU, different Linux kernel, different setup, all that, and it worked just well. More details on that in the paper itself. Okay. So some additional results not shown here, but in the paper, we also went through and recreated sort of the classic linear regression-based HPCs. We also showed exactly what would happen if we used language runtime events for linear models and neural networks. Again, more details on that in the paper, but the idea, since this is kind of the linear regressions, that nonlinear behavior doesn't work out so well, and the neural networks seem to be a bit overkill, at least for what we tried. So in conclusion, Vesta provides a novel approach that uses JVM events for power modeling. It explains power consumption at the application level, right? And it manages to satisfy the principle of least privilege, the idea that we're not going down and looking at hardware performance counters outside of the scope of the application itself. Right? We're just looking at information that can be gleaned from the runtime and from the application. It's low overhead and highly precise, exactly what you want from a power model. Okay. So thank you for listening, and does anyone have any questions about Vesta?
If you could remember to state your name and affiliation. Thanks.
Miliana Sabatovich, University of Maryland. I was curious on your graph showing the mean average percent error.
Mm-hmm.
There's a couple benchmarks that spike a bit higher, right? Do you have any insight as to
Yeah, so we talk about that a bit in the paper. Two of them, so our decision, and we also discussed why we chose this in the paper too, but we had a 1 second bucket for our timestamp data. And we also, some of the benchmarks in the benchmark suites run for like 1/3 of a second. So we weren't really grasping quite a lot about the runtime itself. Since we all, we chose the same number of iterations for all benchmarks, they kind of had less data associated with them. So then for a model, you're going to have less information to train on. So that was for a couple of them. One other, it's possible we have a screening process for choosing the lowest overhead nodes. Again, more on that in the paper. And it's possible that a node or that an event that was very useful for one of the mispredicted lines, the Scaladoku, perhaps that we lost information from dropping one of those events. So that's some kind of indication as to why those didn't perform as well.
Thank you.
Great, thank you for the question.
Matthias Böhm, TU Berlin. So super interesting talk, and you showed those arrows for JIT and GC, kind of how much you mispredict, and you showed the sharp values. But just out of curiosity, what is the absolute value of power consumption of different JIT versions and different GCs? So could you quantify how much % of total power consumption do we actually spend in those meta services of the JVM?
I was saying, like, if I understand the question correctly, the idea of, like, what's the difference between jumping from one model with a given JIT configuration?
No, in general, just out of curiosity, for JDK 19, so how much % of total power consumption do we spend on GC? So not what the error is, but what is the actual absolute value? So just out of curiosity.
So we don't track exactly, like, we don't have any information on that specifically, like in the paper, any experiments that we tried. Perhaps something that could be done. I don't have any information on that specifically.
Okay.
Thank you for the question.
Hi, I'm Kunal Sareen from the Australian National University, and thank you for the interesting talk. I have a couple of questions. So I wonder why you picked USDT probes instead of like JVM-TI events. Maybe this is a slightly technical question. And the other one was, you've done all this great work, but I wonder what insights do you have on what sort of optimizations we can do to actually improve power efficiency of applications and benchmark and programs.
Okay. So I'm not familiar with what was the other?
Oh, it's JVM-TI, JVM tooling interface.
Okay, with those. So I guess I can't say. I can say for the USDTs, the reason we chose those was a decision made a very long time ago. Is the idea that we do have an ability to look pretty low level into what's going on in the runtime. That's why and it's not too hard to get information from it.
Yeah.
In terms of what could be done to manage, have lower power being expended from applications, I think that would have to be further work. I don't know exactly what, say, the developer would have to do in a given instance to tweak one thing or another, some level of measurement, and hopefully the Vesta here provides some kind of insight into, at least we know concurrency, GC, all that stuff, it really does have an effect on energy, and it's very important when it comes to at least this modeling.
Of course. Thank you.
Thank you.
Hi, I'm Luis Pena from University of Illinois, Chicago. Great talk. There was one source of power consumption that I was surprised not to see mentioned, which were system calls. Did you track those at all?
There's prior work, so nothing we did, but there is prior work of using system calls to build power models. The exact name of the paper escapes me right now. But there is work that's been done for that. And we didn't track system calls because we wanted to keep everything inside of just JVM runtime, right? So we didn't want to sort of step outside of, like, operating system or things like that. So that's why we didn't do it. But it has been thought of before, and it is, it's an interesting idea as well.
And a follow-up of that, probably you didn't do it because you didn't have like a probe that when a system call happens would be done.
Yeah,
What other probes do you think you'd like to have that you don't have?
It's an interesting question because there's quite a lot of them. And there are interesting ones that we kind of have to drop because tremendous amount of overhead because they get called all the time, things like method invocations and stuff like that. But yeah, I don't know exactly. I never really thought about like what are we missing from the whole space, because we do find quite a lot of disparate and descriptive probes. But yeah, I don't know exactly what. It's an interesting question of what's missing. I don't know.
Okay. Thank you.
Thank you.
We're running nicely ahead of schedule here, so I'm going to indulge in a question if you don't mind. Yeah, I guess one thing that came to mind for me, and I think maybe Kunal touched on it in his question, was how do you envisage developers using this? Like one application I could imagine is, my thing seems to be a bit power hungry. Why?
Yeah.
And the developer asking that question and trying to use this to look at that.
Yeah.
Is that what you had in mind or not?
I think as the tool exists right now, there's probably limitations when it comes to what a direct developer can really influence. Really, the crucial idea of Vesta is that we can build these power models from language runtime events, right? And maybe in the future have them, have it be more refined and figure out exactly what's doing what, instead of just knowing now that we can do it, I think is what's most important here.
Right. Thank you.
Thank you.
Let's thank Joe. All right, let me introduce the next speaker. Minxiong Jiang is at KAIST, and Minxiong is going to be talking about modular hardware design of pipeline circuits with hazards. Thank you.
Thank you for introduction. I'm going to tell you about our work, modular hardware design of pipeline circuits with hazard. As a background, let's look into the combinator-based modular hardware design. In these days, we are in the golden age of hardware acceleration. With the end of Dennard scaling and Moore's law, the hardware industry is producing more specialized accelerators such as GPUs, TPUs, NPUs, and DPUs. Due to its variety, hardware design requires high productivity. As a result, many productive design tools have appeared. After long domination of Verilog and VHDL, high-level hardware description languages like Chisel and high-level synthesis tools like Xilinx ByteDIS are widely used in the circuit design. Among various techniques, some high-level hardware description languages used ideas from functional programming, such as combinator and type system. In this work, we focused on the combinators. Let me tell you more about combinators. With the functional languages combinators, we can describe hardware circuits in a modular fashion. For the motivational example, let's consider the FIR filter. This circuit multiplies the three most recent values in the input stream with C0, C1, and C2 respectively, and then outputs the sum of these products as our output stream. For example, if the input stream consists of the values 1, 0, and -1 in sequence, the output stream would be C0, C1, C2 minus C0, minus C1, and minus C2 in sequence. So now let's see how to modularly describe the FIR filter. You can see that the filter is composed of three subcomponents. First, it stores the last three input values using multiple registers, or in other words, we are windowing the input value. Second, it multiplies the three input values with different constant values respectively. Finally, they are accumulated into the final output. We can modularly compose these subcomponents with combinators. More specifically, you can construct the module by chaining the combinators. The first window combinator transforms the input value to multiple input values by instantiating registers. Similarly, the second map combinator multiplies the three input values and the constants. And the final sum combinator accumulates the values to produce the final output. As you can see, you can modularly construct the FIR filter from its subcomponents by just chaining the combinators. It makes it easy to understand the data and control flow, and also reduce the error-prone tasks in connecting wires. So the combinators are good, but you observe that their applications are severely limited to simple circuits. For the motivational example, let me tell you more details with the in-order pipe-stage pipeline CPU core. To briefly explain how the circuit processes instructions, let's use this load instruction as an example. In the fetch stage, the circuit accesses the instruction memory to fetch the bytecode. Then in the decode stage, it decodes the bytecode to identify that it's a load instruction and accesses the register file to get the value of the source register. Next, in the execute stage, it performs arithmetic operations such as calculating address values. In the memory stage, it accesses the data memory to read or write values. And finally, in the write back stage, it writes the results to the register file. So we may expect that the pipeline CPU core also would be represented as follows with combinators. However, in reality, they require a global control logic to support handling multiple instructions simultaneously in a pipeline circuit. Each stage needs to communicate with this control logic, so we cannot apply combinators directly to this circuit, and it makes it hard to understand data and control flow. There was a related work that generalized the combinator to decompose the control logic for structural hazard. However, the limitation of this work is that it cannot be applied for data or control hazard. So to address this problem, we generalized the combinators so it can be applied for also data and control hazard. Before we go into our solution, let's look into the related work and its limitations. There was a related work which is applying combinators for pipeline circuits with a structural hazard. The structural hazard occurs when multiple instructions within a pipeline trying to attempt to access the same resource simultaneously. For example, let's assume that two load instructions are being executed and the previous instruction encounters a data cache miss. In this case, both instructions continue to progress until the I1 reaches the memory stage where the cache miss occurs. Consequently, I1 needs to remain in the memory stage due to the data cache miss. Also, since I1 occupies memory, I2 must store in the execute stage too. The execute stage needs to know whether the memory is occupied or not at the next cycle, so the memory stage needs to send this information to the execute stage. And this information can be decomposed using the valid-ready interface. The valid-ready interface is a communication protocol in hardware. When there's a sender and a receiver, the sender indicates whether it has data to send through a valid bit, and the receiver indicates whether it's ready to receive data through a ready bit. When both are true, the sender sends payload to the receiver. So instead of relying on control logic to communicate the information that memory is occupied, we can connect the execute stage and the memory stage using the valid-ready interface. Then by setting the ready bit to false, we can express that the memory is occupied without the need for global control logic. So in our previous work, ShakePro proposed the combinators for valid-ready interfaces. So the circuits with only structural hazard can be represented with generalized combinators. However, their limitation is that the valid-ready interface cannot be used for data and control hazard. The data hazard occurs when the late instruction is dependent on the previous instruction's result. For example, this example writes the results to the R2 in I1 and read the value of R2 in I2. Then both instructions continue to progress until the I2 reaches the decode stage where the read of R2 occurs. Here, I2 needs to remain in the decode stage because the result of R2 is unavailable now. And in the next cycle, the memory stage can bypass the result of R2 to the decode stage, and now I2 can continue to progress. And control hazard is another type of hazard which occurs when the misprediction happens. For example, this example mispredict the next PC from the branch instruction. When the misprediction is detected in the execute stage, then it needs to send the discard information to the decode stage and send the correct next PC information to the fetch stage. So to deal with this data and control hazard, we need to send these signals to backwards through the control logic. However, these values cannot be expressed with the valid read interface with two reasons. First, the backward signal needs to be wider. For example, the information that memory is occupied can be expressed with a 1-bit ready signal. However, the information needed to resolve data hazard, such as value of R2 will be 42, requires more than 1 bit. Second, the transfer condition needs to be more flexible. For instance, to express that data should be communicated when memory is occupied, but not when R2 is not ready, we need to be able to send the information that the required register address is R2, which requires more complex condition. So we generalized the valid read interface to address this problem. We defined hazard interface by generalizing the valid read interface. First, it allows sending resolver signal, which has arbitrary type instead of just 1-bit ready signal in the backward direction. Also, we can express the receiver is ready in the transfer condition as a ready function, which takes payload and its resolver as an argument. With this hazard interface, you can decompose the control logic to represent the data hazard as mentioned earlier. For example, the execute stage sends the address of the register being processed later and the data value that can be bypassed to the decode stage as backward signal. Then the payload can be transferred if there is a data can be bypassed while there is no stored. We also provided syntax for defining the hazard interface so that it can be used in the code. Users can specify the type of payload and resolve for the hazard interface. They also are able to write a ready function that takes payload and resolver as inputs and outputs the Boolean value, which represents the ready condition. This definition is quite general. For example, valid read interface is an instance of hazard interface. In here, the type of resolver signal is just Boolean value, which corresponding to the ready bit, and the ready function is just the resolver signal itself. And it can also be used to represent the interface between the decode stage and the execute stage. In here, the resolver signal contains bypassed register's address, which has type U8, and bypassed register's data, which has type option of U32. The ready function here checks there is a bypassed data while it is not stored. Using such hazard interfaces, it's possible to represent a pipelined CPU core by decomposing the global control logic into combinators. Also, each stage is further decomposed into more primitive combinators. Now we evaluate the case studies on 5-stage CPU core and 100 Gbps Ethernet NIC. First, we conducted experiments with 5-stage CPU core. We compared the original Sodo CPU core in Chisel and its port with hazard interfaces in performance, power, and area. For performance, we simulated the CPU core with CoreMark and Masood benchmarks. We observed that the CPI is exactly the same as original design, and ours consume less area and power than original design. But maximum frequency is lower than original design. We believe that this trade-off is due to our compiler optimization, and more details are on our paper. Next, we conducted experiments with 100 Gbps Ethernet NIC. For performance, we compare the original quantum in Verilog and each port with hazard interfaces in throughput and resource consumption. For throughput, we measured on real hardware with TCP/IP and file serving benchmarks. We observed that the hazard interface version consumed 6% more lookup tables and 3% less flip-flops in an FPGA. And for the throughput, there was less than 2% difference between the original design and our photo of it. So hazard interface doesn't incur significant overhead of resource consumption or throughput in various benchmark configurations. It's quite expected because you can precisely describe RTL circuits in hazard interfaces like in Verilog or VSDL. In conclusion, our key contributions are generalize valid rate interface to hazard interface and propose primitive combinators for hazard interface and apply combinators to pipeline circuits with hazard. Additionally, the paper includes more details such as primitive combinators, CPU implementation example, type systems for combination loop detection, and so on. Thank you for listening.
Thank you. We have time for questions. Okay, I might ask a question. If you go back to your first performance comparison.
Yep.
Just back one. Yeah. Oh, yeah. So I just got a little lost there, and I wasn't sure. So you're at ours, and you've got Sodor. What exactly is the difference? Yeah, can you just explain more exactly what you're comparing here?
Yeah. So we, I think I have enough. For the performance, we simulated the CPU core test bench with some RISC-V test benches in cycle-accurate simulation, and in result, the CPI was same as original and our photo of it. And for the power and area, we used some open source ASIC flow, and we synthesized the two designs. And in power and area, our power and area was less than the original design, but the critical path was larger than the original design. So there is a trade-off of it then.
Okay, thanks.
Yes.
Hey, it was a really nice talk. So I had a question about the loop detection part. So like if you are able to figure out that, so can you do further optimizations on loops? Like circuit loops, or maybe like you see repetitive patterns of RTL, so can you try to roll it into a loop or unroll some repetitive operations into a single?
Currently, actually I did not think about it, but our target was on describing the microarchitecture. So
Okay.
there is no loops in the code.
Okay.
Yeah. So I think I need to think about it more.
Okay.
Yeah.
I'll talk to you offline. Thank you.
Thank you.
Hi, I had a question about the whole combinator part you proposed. Do you have like a working? It wasn't really quite clear to me if you had like an actual like working implementation of that in a very specific language, and if so, like what are the like things you're targeting? Like, are you sort of targeting system Verilog like other generators, or are you sort of like how? Yeah, just to know how you're actually doing the like comparison to other implementations.
Actually, we built a domain-specific language which is embedded in Rust.
Yeah.
So, and then users can write code in Rust. And we implemented a compiler that transforms the Rust, our DSL, to the Verilog. And we used that generated Verilog code as an input of the synthesis tools such as Vivado, and yeah, we compared in that way.
Oh, okay. Yeah. Thank you.
Thank you.
Okay, let's thank our speaker.
You can recognize me now. We on? Okay. No, it's going. It's thinking.
All right. Our next speaker is Tom Ball from Microsoft, and he's going to talk to us about JACDAC, service-based prototyping of embedded systems.
Yes, hello. Everybody can hear me, and I am pleased to represent this work by the JACDAC team. It's done over the last 4 years or so, including a number of people from Microsoft and Steve Hodges, who is now at Lancaster University in the UK. So we heard a lot about Moore's Law today and through the years. I'm going to tell you a little story about that and JACDAC and how we got to this weird plug-and-play system, which is actually commercially available and will be handed around for you to try. A very interesting sort of demo. So Moore's Law has enabled just so much. At Microsoft, we piled on features and features in the software. We got layers of abstraction. We're able to virtualize pretty much every piece of hardware known to man because computers are so powerful. And people think of it as over, but on the low end, it's not. So microcontroller-based technology, which is low power, low cost, is actually several generations back. And it's getting more and more powerful, smaller. And so Moore's Law is not dead. Think about prototyping with microcontroller-based technology. It is really stuck in the 80s. We have I2C, SPI, fiddly wires, fiddly connectors, and especially if you're trying to get new people to start working with microcontrollers, it can be quite a bit of friction. So the basic idea of JACDAC, very simply, is to use extra silicon close to devices, like even buttons, plus a modern software stack to make it easier to prototype embeddable devices with microcontrollers and to make that as widely available as possible. So the overview of the talk, I'm going to give you a little background of where I'm coming from. Over the last 8 years, my team at Microsoft has worked with the BBC, and we've created a system called the microbit with a programming environment. The microbit is a small board, and it's very low cost and high quality, and the programming environment and the materials for teachers make it simple to learn and use, and it's been around for 8 years now, primarily in middle school. As software engineers and software engineering researchers, we also want to make the experience extensible, and that's where we sort of give it a thumbs down. So JACDAC, you can think of it as plug and play for microcontroller-based technology, much like USB allows us to plug things into our computers every day, and it just works, mostly. So what is this idea of physical computing? Physical computing is actually the term that educators use for software and hardware that senses and responds to the real world. So in PLDI talk, that's embedded or reactive systems generally. Maybe not hard real-time systems, but anything that can sense environment, the light, sound, and can react to it through actuation, that can be a physical computer. And that's a great way to actually get many types of people engaged in computing through things that actually move and shake and make sound. Yeah. So one physical computer that came out in 2016 is the BBC Microbit. I'm actually showing you here version 2. It's about half the size of a credit card. On the front side, you'll see an LED screen, 5x5, so very high-res graphics with 2 buttons, A and B, and an edge connector at the bottom. On the back, there's a whole bunch of things like a compass and an accelerometer. There's a radio antenna. It speaks Bluetooth and a lower-level protocol, essentially UDP. It has a microphone and a speaker, and it has a processor now with a whopping 128 kilobytes of memory. That's 3 times what my Apple II from 1981 had. It goes a little bit faster. I think it's clocked around 64 megahertz, and it has half a mega flash. So it's an awesome computer to learn with, and it's visible, unlike many of the computers that are sealed away in consumer products. The Microbit is a visible computer. And what can you make with it? Well, since it's battery powered and very low power usage, you can strap it to your foot and you can make a step counter. You can make a rock, paper, scissors game where you shake the Microbit and play rock, paper, scissors against your digital opponent. You can also make crazy robots that respond to light and actuate servos. So, you know, the microbit is a little embeddable computer that can be programmed, and there's a lot of creative uses. Here we're showing the microbit in a radio control car situation. So you have two microbits, and the accelerometer on the one in the person's hand is being used to send messages to the microbit, which is, you know, driving the car. So you can also do sort of remote control and that. We premiered the microbit, we premiered in the UK in 2016. Since then, the Microbit Education Foundation is a nonprofit that took over the brand. Its goal is to inspire every child to create their best digital future, and there's over 8 million microbits distributed worldwide today in over 60 countries. The cost of the microbit is under $20, so it's quite cheap, and they're commercially available, so you can find them pretty much in Amazon or everywhere. My team at Microsoft, we created this platform for programming microcontroller technology using web apps. So no C compiler required, no download, no install on a computer by an IT admin. And then we've with partners, we've surfaced several websites. The web app basically has a full IDE with both block-based programming a la Scratch and JavaScript, and you can go between blocks and text-based coding. That's novel. It's all written in TypeScript, and it features both hardware simulation and a compiler all the way to ARM machine code in the browser linked against a pre-compiled C++ runtime. So that once the web app is loaded, you're good to go. There's no call out to a C or C++ compiler. And we've actually got a number of different websites that are hosting different types of microcontroller-based hardware. On the left, the microbit; in the middle, the Adafruit Circuit Playground, and then we have a special thing for retro arcade games on the right that's near and dear to my heart. The principles of Make Code are to really simplify making and coding with microcontrollers, meet educators and students where they are, which would be Chromebooks, Mac OS, Linux, Windows, whatever has a modern web browser. How's that for Microsoft? And support progression to a wider world of programming languages such as JavaScript. We also support Python. And really this idea of actually extending beyond what's possible with the microbit to peripherals. And that's where this idea of extensibility comes in. So let's go to a demo. I will very quickly show you what it's like programming inside Make Code. And for some reason, we are not seeing that on the screen. No, I don't know. It has not happened. Usually I'm just duplicating my screen. Let me just duplicate. We're good? Okay, I'm getting out of that, and I have no idea why we wouldn't be seeing this. Okay, there it is. So Make Code, this is Make Code with a little program that I've created, which basically has 3 blocks that you can drag out. On button A, we show a heart. When we press the logo, we clear the screen. So I can do that by touching in the simulator here. And then on button B, we do something different. We show the current temperature. And of course, what's the temperature? Well, it's actually simulated here. So the current temperature, let's drop it. Let's drop it to the single digits and press button B again. It's now 7 Celsius. Brr, I'm cold. Okay, so this is essentially the programming environment. We can go to JavaScript. We can actually do text here. We can go back to blocks. There's a whole bunch of features I can't get into. But extensibility. So let's say I'm a teacher, and I'm like, oh, this is great. I have this ability, but I want my students to learn about the environment. So what hardware is out there? So we go here, and we search in the extension dialog for environment. We see all these partners who have all this cool hardware, and we click on one, and now it's loading an extension, a library, into the environment. And now I can see here, oh, you know, I can get the air and weather, and oh, I can get, oh, not just temperature, I can get humidity. So let me drag humidity and put that there instead, you know, and then run my program. And now we sort of see the problem. We get like a question mark, right? That hardware, we don't know about the hardware, we just have some code. And that code basically like is, oh, you read the temperature from this GPI pin, or you read it over I2C. But we don't have support for that. So whenever we add hardware to the mix, unless we special case stuff, this whole beautiful experience of coding with the simulator and then downloading the code, which I haven't shown you. There's the compiler. We can download its file, and now that compiler in the browser is being invoked, and voila, we just got a hex file which we could drag and drop onto the device. So the problem there is that we've got extensibility in the software domain, but not in the hardware domain. Okay, and that's really where we come back then to JackDAC, which is this plug-and-play system. So we think of USB as an exemplar of plug-and-play. Why? You have standardized cables and connectors. You have dynamic discovery and composition with devices, and you have abstraction over common devices. The cons are that USB is not really a true bus. Connections are point-to-point. A host is required for direct communication. And the cables and connectors are much more bulky and rigid than what you find with prototyping. So it all leads to higher cost. So with JackDAC, what we're doing is trying to get a lot more pros. We got the first three things: standardized cables and connectors, discovery, abstraction. But we have a true bus architecture, low cost relative to USB, and a very easy programming paradigm, as you'll see. The cons are low bandwidth. It's 1 megabit per second. And there's an increased cost on the edge, as you'll see. But it's very low, about 3 cents for an 8-bit PDAC processor. So the JackDAC connector and cable are shown here. It's built into the PCB, so it's part of the PCB design. It's got ground, power, and data. The data is the short one. It's double-sided. So then the connector, the cable, it doesn't matter which way you put the cable in, it connects, and here are the cables. The modules are very simple. They range from buttons to sliders to a light detector in the middle, and you'll see the JackDAC connector on each of them. Furthermore, you'll see a very tiny little integrated circuit. That's the PDAC. That's the extra silicon we're spending to actually have each device be able to advertise itself on the bus. Okay, so what I'd like Blake to do is plug the battery in to the device we have there, which has been loaded with a little jukebox program, and you can hand it around and try plugging and unplugging devices and play with them and see what happens. You've got the microbit, essentially. What is being handed around there is the microbit with an adapter to JackDAC, and then this is the cable, and you can see the plug. So please hand that around. Feel free to play with that. Okay, so this is a really weird idea, but we view JackDAC as a client-server architecture where everybody's on the same bus, and there can be both modules, which are servers. Like a button is a server now that says, I'm a button, I can be pressed, and you can use me. And then there are brains, our clients, that are the user level programs. So in the case where we use JackDAC with the microbit is the brain, it's the client, and then we have a true bus, everybody's on the same 3 wires, and the modules at the bottom, here from left to right, an accelerometer, a light sensor, a slider, and an LED ring, are the servers. Okay, and they're all advertising themselves and saying, hey, I'm here, I'm alive, and this is the service that I represent. So if you think of this in terms of an OSI stack on the left, JackDAC has a number of similar levels to OSI, but we've defined from bottom up an electrical or a manufacturing and mechanical design, electromechanical attributes, and electric. That's for another paper. The PLDI paper focuses on really the software design and the stack. And then there's another paper where we performed a user study. So that is at a very high level the JackDAC architecture. It's client-server. There's a bus. We send packets back and forth asynchronously. And for more details, ask me questions at the end or see the paper. What I want to do now is give you a little bit more of a demo about JackDAC. And I see it's making its way around. So that's great. I hope everybody gets to see it. So let us do a demo. I'm going to go to the JackDAC website. So here's the JackDAC website. We can see it. So the microbit has a USB connection. So the JackDAC bus can be extended from the 3-wire protocol we have on the physical circuit over web USB into the web browser. And this is what I mean when I say that JackDAC has a modern stack. So again, with MakeCode, we we don't want a C or C++ compiler to be installed. Similarly with JackDack, we don't want device drivers and all that stuff to mess up the user experience. So what we're doing here is we've plugged the microbit in, and we're going to connect it over web USB to the browser that you see here. And actually, it's already connected. So what you see here from left to right is that we have a light sensor. So the light sensor module is here. When I cover it up, the digital twin on the left is showing me the value. So the first thing we have is discovery. If I take the light sensor out of the bus, eventually, it's going to disappear there, and it has disappeared. I plug it back into any of the ports, and we are good. Okay, I have a slider, and the slider goes back and forth. JackDack services are the abstraction by which all this happens, and I will give you just a brief tour of that. We have a service catalog with the abstract services defined in a mix of Markdown and syntax defined in the PLDI paper, and that is shown here. So that the accelerometer is actually a register with 3 values, and you can see that we actually have units of gravity. We have the actual wire data value here specified. Furthermore, we have events. So a module can raise events as well as exposing registers over the network. You can also send commands to modules as well. So the JackDack website has a whole set of devices, many of which are commercially available, as well as the tooling for device manufacturers to learn how to create new modules. So finally, I want to end with a very quick demo of how this gets then exposed in Make Code. So let me do that. So we're back in Make Code, and what we're going to do is we're going to attach to the microbit, and basically what's going to happen here, hopefully, is that we'll see the JackDack stuff. Oh, too bad, too bad. All right, we missed out there. All right, let me finish up, because I think we're running out of time. Are we back? Right. Okay, so we've built a number of JackDack projects internally. We had an accessibility hackathon several years ago, some examples there. Just in summary, JackDack plug and play for prototyping with microcontrollers. We've sought to retain the low-cost, high-quality simplicity with the microbit, but extend it to a plug-and-play system. It's applicable to other platforms. We have adapters for Raspberry Pi and other hardware. It's all open source, both the hardware design and the software, and it's commercially available via third-party manufacturers. So thank you very much.
Thank you, Tom. We do have time for a question or two. All right. Have we got one coming from? No. All right. I'll happily ask a question.
Okay, cool.
That was an awesome talk. Very inspiring. As a long-time PLDI person, when you reflect on that project, what were the key PL-ish challenges that you found in doing that software stack you spoke of?
That's sort of an interesting thing. I think the big thing about JackDack is many design decisions together, right? The language itself is an interface definition language. Part of the design goal there is to have a wire format that translates very easily to packets, right? And at the same time, have enough high-level abstractions in that so that we can generate the client code. So part of the language design was to sort of bridge this gap between wanting nice client code, event handlers, and things like that, but also supporting sort of the description of on-the-wire format. And then, making that really optimizing the runtime and everything to work with, say, very low cost and low memory microcontrollers.
Great, thanks.
Hi, thanks for the talk. I thought that was great. I have a question. Do you have any sort of knowledge or experience of how people transition from using these sorts of tools, and particularly the programming environment, to more like real programming or electronics?
Yeah, that's sort of interesting. I guess one way to look at it is, if you wanted to produce, like, if you did some prototyping and then you wanted to produce 10 or 100 of a device, you wouldn't want to do it with all these cables, perhaps, right? So then you would need to, you know, perhaps produce a single PCB with all your components on it, right? So it's not just a matter of programming. I would say it would be a matter of also figuring out, you know, how to optimize your design, right? So we do have some research projects around that. So given you've done prototyping with JACDAC, how do you take the set of things that you want and make a device? In terms of the programming, our programming model is very much at a high level. It's event-based, and we hide a lot of the asynchrony from the programmer. So we have an underlying operating system, which is cooperative coroutines on a single processor. There's a lot of complexity hidden from the end user. If you want to start doing more things that are hard real time, you know, you're going to have to learn. You're going to have to go down a few levels. So the type of things you build with us will get you only so far, and then you'll probably hit a wall. Is what I would say. The truth is, yeah.
Okay. Thank you.
Sure.
Time for one last quick question.
I don't know if this one is easy to answer, so maybe this one doesn't fit in the time. But I'm curious, I mean, it's had such a long history. I'm curious if there's something that when you tried revealing it to users, especially to kids, that ended up being sort of the most confusing and that you felt really had to be hidden under abstractions.
Oh yeah, it's not up here anymore. There was a super confusing thing. When we connect make code to the bus, originally we had 2 microbits on the bus. We had the real one and the virtual one, and both of them can be a brain. So now you've got all these devices, and you've got 2 brains, and which one's in control? So this caused a lot of confusion. We had a lot of design discussions, and then we have a partner, Forward Education, that basically helped us out. So really, there is this big confusion that can happen when you've got the ability to put virtual devices on the bus as well as physical, and then you got a mix. So what we've currently done is, like, when your microbit is attached to the bus, the physical one is sort of the one, and then the microbit, the simulator, is sort of a pass-through. Okay. But you know, there's a huge like design space there that's relatively unexplored from our viewpoint, and that was like we did a lot of trials with teachers and saw major confusion. It's like only one brain at a time.
That's really cool. Thank you.
That was the lesson. Yeah. Okay.
Thanks, Tom.
Thank you.
I'm plugged in. Okay.
All right, our next speaker is Blake Pelton from Microsoft, and I love this shirt. And Blake is going to speak to us about Kanagawa. Wavefront threading enables effective high-level synthesis. Thanks, Blake.
Thank you. Kanagawa is a hardware language at Microsoft. It's been sort of internal up to this point, developed for many years, but we plan to open source it. It's a big thing. I'm really going to focus on the threading model today, which I think is the key novel aspect that we described in the paper. So I'm going to talk a little bit about the design goals, spend most of my time on the threading model, show you just a taste of the results, and talk about open problems that would be interesting for collaboration. So it's a typical hardware thing. You have high-level source code coming in, you give that to the compiler, it gives you synthesizable system Verilog, and then you can feed that to a standard tool for FPGA or ASIC implementation. At Microsoft, IP generated by Kanagawa is broadly deployed on FPGAs in the data center. So we have 2 design goals for the language that are really relevant here. The first is that the code should be high-level and abstract, and there's 2 pieces to that. The first is that the language itself is missing unnecessary details, all the tedium is sort of removed. The second is the language enables the development of abstractions in libraries, which then makes code that uses those libraries itself more abstract. The second is the language should be easy to reason about. You should be able to look at the code and talk about the performance and the correctness and be pretty confident in your predictions. So I've been on this project a long time. One question that has eluded me, and I think might still elude me, is what exactly is a hardware description language? I found this description from a paper on Verilog, which says HDL is a programming language with special facilities for dealing with the problems of hardware. One of those special problems in hardware is parallelism. And so an HDL is a language that really lets you use the parallelism that Moore's law gives you. And that sounded good, except for now you think about it for a minute, and that's really quaint, because it implies this world where the hardware people deal with parallelism and the software people deal with sequential code. And we all know that sort of fell down. And I was going to talk a bit more, but then insert the keynote from day one here. And David Patterson described it as the hardware industry throwing a Hail Mary pass in American football, hoping the software engineers would catch it and be able to sort of shoulder some of the burden of dealing with parallelism rather than hiding that all on the hardware side. So the idea with Kanagawa is let's complete this circle. If shared memory multithreading is a standard paradigm that seems to work well, it's a cliche maybe for this audience, but it works well for people writing imperative code to sort of take on some of this responsibility of utilizing parallelism. Why don't we just try that for hardware itself? And so we'll express shared memory concurrency in the language and map that directly to hardware. And that's the way we utilize the parallelism of hardware. So the secret sauce to make this work is our special threading model, which is a lot like standard multithreading, but there's a key difference, and that's what I'm going to describe now. That's where I'm going to spend most of my time. It both makes the mapping to hardware very straightforward, so the compiler can be simple, and therefore you get very predictable performance, and it's also much easier to reason about at the source level than traditional multithreading. So our threading model, we call it wavefront threading. Here's some just standard Kanagawa code. It just looks like regular old imperative code. You could say this is C++ or something like it. So here's a thread, the blue thread that comes and starts executing code in this function at some point in time. And it moves down through the statements. And at some point in time, another thread, the orange thread, comes and starts executing. With wavefront threading in Kanagawa, we can say the blue thread is ahead of the orange thread, and that's the phrase we use in the paper. And that relationship stays constant over time, so the blue thread will stay ahead of the orange one. And there's all these details you can read in the paper about how that ahead of relationship relates to control flow constructs in the language. And that was a bit hand-wavy. You could say, what is it exactly they're executing in order? Is it lines of code? Is it statements? What is it? And the answer is it's access to shared state. So every variable is either thread local or it's shared between threads. And it's the accesses to the variables that are shared between threads. That's what executes in order when you get down to it. So if you really want to be precise, you call this a memory consistency model. And there's two parts to the definition. We call it wavefront consistency. The first looks like what you would see in a definition of sequential consistency. And that is, from the point of view of a given thread, all the accesses occur in program order. The second, here's our secret sauce. If a given thread is ahead of another one, and they're both going to perform the same shared memory access, then the thread that's ahead will perform the memory access first. This is it right here. This, if you want to boil Kanagawa down into one thing, that was it right there. And I'm going to spend a few slides with some animations describing this. So on the left here is just, it's valid Kanagawa code. It's just a boring old sequential loop. And on the right is a graph depicting sort of the dependencies here. So in each column is the statements for a given iteration. And then the rectangles represent each statement. And then we have the edges. So the vertical edges represent the requirement that for a given iteration, the statements run in order. The edges that go between the columns say that a given iteration cannot start until the previous iteration finishes. And this is just the standard semantics for a sequential loop. Many languages have parallel loops, which remove the dependence between the columns. And you can say each iteration is run by a different thread. Or another way of saying that is, any thread can start this at any time at once. Any thread can finish. They can overtake each other. It's kind of the Wild West. And this, again, on the left is valid Kanagawa code. Now here we go. Here's a pipeline loop. We call it pipeline 4. Similar thing. We're saying, here's a loop. Here's the loop body. I'm going to spin up 3 threads that'll execute the loop body. But I've got these right arrows in the control graph here. And those are the requirements from wavefront consistency, our consistency model. So what they're saying is, like the first statement, it must be run by iteration 0 first. So here's an example. So like the blue thread is doing iteration 0. It has to go first. There is no choice. Once it moves down to the next shared memory access, and on this, for just simplicity, I said every line has a shared memory access. That sort of makes room for iteration 1, which is processed by the orange thread. And once it moves down, that makes room for iteration 2, which is processed by the purple thread here. And so what this does, it illustrates is that our memory consistency model gives us this inherently pipeline semantics, where threads flow from the top to the bottom through the imperative code, and they stay in order. So now I'm going to spend a few slides talking about how this maps to hardware. And the point is, it's a very obvious, straightforward, predictable mapping. You're not relying on the compiler to do really anything smart or a global optimization. So here's how just a sequence of straight line code maps to a pipeline. On the left is the code, the right is the pipeline. Here's a thread that enters. That plus might be scheduled on the first pipeline stage. Then it moves down to the next line of code, which has another plus that'll be scheduled on the second pipeline stage, same colors as before. And so on the left, you see the threads flowing through the statements. On the right, it's data flowing through a pipeline. Pretty straightforward. Now we're going to talk about control flow. So here's a sequential loop. And on the left, I just said body as a placeholder. That means whatever the body is. On the right, here's the hardware. And the purple rounded rectangle is, again, sort of a placeholder. It means whatever hardware would be generated by the body of the loop, whatever it is. A sequential loop is essentially just this backward link. It says when a thread gets to the bottom, it makes a choice. Am I done looping, in which case I keep going down, I leave, or I return for another trip around the loop. Now here's a pipeline loop, again, pipeline for, that's the same construct we talked about before. So when we start running a pipeline for loop, there's a little FSM in the hardware that will dispatch the threads. In this case, it's 2 threads. Then whatever is the body of the loop, and then at the bottom we have a little FSM that collects those 2 threads and sort of waits for them to both get there. Pretty straightforward. Now we're going to talk about composition. So here's, again, the same hardware for a pipeline loop. I'd switch the body to green. And remember, the body green is a placeholder. Here's a sequential loop. Again, same picture I showed you before. And now, very straightforward. Take that thing on the right and substitute it in where the green rectangle is. And that's how you say a sequential loop nested inside a pipeline loop. And the point is, the hardware composes in a way that's very analogous to the control flow. And the programmer just gets this in their mind and says, oh, I understand how the hardware is going to compose just like the control flow is, and therefore I can predict my performance very accurately. And at no point in this process is the compiler doing an optimization like, here's a sequential loop, but I realize I think I can pipeline it and get better performance while maintaining the illusion that it's running sequentially. And sort of, if that optimization works out well, you get great performance. If that optimization fails, you get horrible performance. That's not the model here. The compiler is very straightforward. And if you want good performance, essentially you have a lot of threads. If you have a lot of threads, your hardware is highly utilized. In addition, well, yeah, fine, here's nesting the other way around, where you have a sequential loop that contains a pipeline loop. Similar thing, it's just we've moved that backwards edge to around the outside. And finally, just to like beat this dead horse, here's a loop right after another loop. And so there's a pipeline loop on top and a sequential loop on bottom, and there's the hardware you get. It's all very straightforward. I think from a software point of view, this is like duh, obviously. But from a hardware point of view, it's kind of a novel thing that you just get this predictable performance and composition from imperative code without the compiler doing really heroic work. So if you combine this predictability and the ability to compose things with predictable performance with well-established techniques from imperative and functional programming to write composable code, it enables the development of a horizontal library. And an example of this, like the pipeline for and the parallel for functions I showed you before, those are actually library functions. When the code is open source, you can go see the library is actually quite large, and it's horizontal, like the STL and C++. It's not like, here's the graphics library and the compression library. It's more like general algorithms and data structures and utilities to let you compose code. I'm going to spend 3 slides talking about the difficulty of reasoning or the ease of reasoning about this as compared to traditional multithreading from 3 different points of view. The first was inspired by this blog post by Hillel Wayne, who said, don't make fancy arguments about psychology and how hard it is for humans to think about things happening at the same time. Just count the number of possible executions for a piece of code. And if there's many possibilities, it's hard to reason about. And if there's few possibilities, it's easier to reason about. In terms of the graphs I've been showing, what you want to think about is how many ways can I topologically sort these graphs. So on the left here is the graph for a parallel for loop, and on the right is the pipeline for loop. And I think it's pretty obvious on the right, there's many, many fewer ways to topologically sort that graph than on the left. For example, like I said before, when you topologically sort the graph on the right, there's only one option. It's the I0 thing in the top left. That's the only option. Whereas if you're topologically sorting the thing on the left, any of those rectangles at the top are valid. So there's just fewer possibilities, which makes it easier to reason about. Another standard technique for many languages is to reduce the number of possibilities, is to combine multiple statements into a single atomic statement they can't interleave. And we have that as a first-class feature in Kanagawa. We call it a scheduling constraint. And here's an example of one type of scheduling constraint, the atomic block. From the language point of view, this means one thread at a time in the block, and there's no torn reads or writes. From the hardware point of view, it means all that code runs in a single pipeline stage. And we have another more general way to express scheduling constraints. Here's the last sort of putting it all together. I'm going to give you a big example, but it's a simple idea. It's the idea, you can say I have a group of threads, and I can say this one's the first, and this one's the last. And that property stays constant over time. And you can reason about that and use just that as a synchronization construct. And it really simplifies the reasoning about multi-threaded code. So here's another library function we have called pipeline last. Again, it models a pipeline loop, but it can return a value. And the value it returns is the value returned by the thread that handled the last iteration. So just describing sort of the semantics of this pipeline last function, you can only have this if you have the notion of a thread that is the last one. And that property of being the last one stays constant. And you'll see in the body of the loop here, there's this isFirst variable where a thread can determine very easily, am I the first thread in a group? And then that property stays constant over time. And in the atomic block at the bottom, it uses that property to say, if I'm the first thread, I will sort of clear this shared accumulator variable called sum. Whatever was there before, I'll just ignore it and clear it. And all the other threads, they just add to it. And so it's this very simple concept of saying threads have an order, they stay in order. And I can use that itself as a synchronization mechanism. All right, I'm going to talk about, there's a lot of results in the paper, a lot of them comparing Kanagawa code against handwritten RTL. Though I'm going to talk about the one I'm most proud of here, and this is a pipeline processor. So here's a quote from a paper in 2019 that says, if you write an instruction set simulator or an interpreter and give that to an HLS tool, you're not going to get good performance. And I think this is very true for industrial HLS tools. And the point is it's a pretty tricky problem. You have to sort of speculate about branches. And your source code is sequential. And so you're putting a lot of responsibility on the compiler. And one tact you could take with this is saying, well, the compiler's not smart enough. Let's stick with a sequential language and make the compiler even smarter. But the tact we take is say, let's write a multi-threaded instruction set simulator with this wavefront threading. And it's not one thread per pipeline stage. It's one thread per instruction. And the threads flow through the pipeline. And if you do that, the code is really elegant. It's concise. It's abstract. And it's very parameterizable. And if you compile it as a soft processor on an Altera FPGA, you get good perf. So we have a RISC-V processor. Against the Neos 5 from Altera, perf per area, it does very well. You could say the Neos 5 is kind of new and not mature, and it will get better. If you want, you can also compare against the Neos 2F, which is a much more mature implementation from Altera, but different instruction set. So it's a bit apples to oranges. If you do that comparison, they're head-to-head. But the Kanagawa one, the source code is just beautiful, in my opinion. So I'm just going to make sure I hit all the points. Yeah, so this is kind of a real thing. We've transitioned from science project to real thing. Engineers at Microsoft are willing to take a bet on it for FPGA accelerators, and it is IP generated by our tool is broadly deployed on FPGAs. We've got this very broad horizontal library made possible by the fact that you can fearlessly compose code. And you can compose code written by different people or at different points in time. And we plan to open source it. I'm going to summarize here with just some open problems that we would be interested in collaboration on. The first is, can you compile this wavefront threaded code to other architectures? It is easier to reason about than traditional multi-threading. And you could imagine saying, OK, one of these Kanagawa threads, I'll fill my SIMD lanes with it, just like a GPU fills its SIMD lanes with threads. Or you could say, I'm going to utilize my cores in a many-core processor, or I'm going to use my nodes in an HPC cluster. I think if this worked out, open question, it would be really powerful because, again, the source code is much easier to think about, and you just have much less chance for race conditions than traditional multi-threaded code. Another aspect here is machine understanding. Compared to hardware, there's a lot of details missing. And so I would think machines could do a better job understanding and generating the code. And again, compared to traditional multi-threaded code, it should be easier because there's fewer possibilities. So we had one successful intern blaze a path here and find some promising directions. on the formal verification point of view, like how you do formal verification of Kanagawa code at the source level. And then it seems really interesting to look at large language models generating Kanagawa code. There's additions to the language. Our general philosophy is don't make the compiler smart. Extend the language. If we find some problem, like some circuit you can't express or some inefficiency, we find a way to extend the language to solve that problem rather than add heroics to the compiler. So I've got some examples of here. Some of the things I heard yesterday were inspiring, like the Descend talk. I think that something like that might be relevant. And finally, there's improvements to the tool chain. So I wrote up here the automated ECO support. There's a lot of them. If you don't know what an ECO is, you can come ask me afterwards, and I'll explain the gory details. It's a bit scary. That's it. Thank you.
Great, thanks, Blake. Questions?
Thank you for extremely exciting work. And I have several questions, but I would say most of them for offline discussions. My primary question is that how do you deal with dependencies among multiple threads or headers between multiple threads?
Headers? Is that what you said?
Yeah,
oh, hazards.
Yeah.
Yeah, the processor is the perfect example. That's why I chose to show it. Because you can't do a good processor unless you can handle control dependencies and data dependencies. Or hazards, I mean. Yeah, and the way they're modeled is shared state. So you have some variables that are local to each thread, and each thread logically has its own copy. You have some variables that are shared between threads. The way all the hazards are handled with these shared variables. And when you write to them and you read from them at the correct point, and you use the scheduling constraints like I showed. Yep. That's the way to do it. And in the library, we have all sorts of synchronization objects, like what you would see in software, like mutex and semaphore, built on top of those.
I see.
Hi, you presented that there are like two ways, like there are multiple ways to have your your for loops, and you presented sort of like the pipeline for and the parallel for, and I was wondering, since this is sort of mainly for HLS, what was the benefit of also keeping that like parallel for?
Oh, so pipeline 4 has a perf ceiling.
Okay.
The perf ceiling is 1 thread per clock cycle.
Right.
Which can be a lot of perf, because if you have a deep pipeline, 1 thread per clock cycle, that's a lot of work per clock cycle. But if you need to exceed that ceiling, then you use the parallel version. And in the parallel version, you don't get this ordering. Things are unordered between them. So a typical use case is, I'll generate one pipeline. It might be 500 lines of Kanagawa code all up. And that's pretty good. And I get most of my parallelism there, just in the pipeline parallelism. But then I might do 2x or 4x replicas of that, because I need 2x or 4x more perf, and I'll do the parallel version there.
Right, okay. And in that case, you would use sort of like the semaphores and locks you have access to in the library?
Yes.
Or, okay. Thanks.
Hi, Jane Chen from University of Cambridge. Thanks for the excellent talk. I got 9 questions, but I'm going to ask the first 2. So you mentioned about the fixed order of the memory access for each thread based on their starting order. That's quite interesting. In other cases, like in softwares, like P threads, like the user wanted to make memory access out of order and then synchronize them using locks. Is that supported in this Kanagawa?
That's the parallel version. So if you use the parallel loop, then you have no ordering that you can rely on, and you have to use locks.
I see.
But typically, you get you write most of your code with the ordered version, and it's just much, much easier to think about.
I see. Yeah, thanks. And the other question is, I find this language very interesting. I want to try play with it. Good. So if I write a simple program in your language and it generates system Verilog, how do I test my system Verilog?
We have an interpreter. That's the simple way, and you don't have to go to Verilog for that.
Is there any way I can generate a test bench as well, like to test the hardware design?
Can you generate a test bench?
Yeah.
So I mean, a typical thing, you write, for small stuff, you write the test in Kanagawa itself, like in a separate file. And then you can either run that in the interpreter or generate Verilog from that.
I see.
That's very common. We have actually a unit test framework in our libraries.
I see. Got it. Thanks.
Yeah, thank you for the talk. My question was about the different for loop combinators you have. So are those primitives, or are they just defined in Kanagawa and you could find different?
The sequential for loop is part of the language. The pipeline for, pipeline last, parallel for that I showed you are actually library functions. If you look at them, they actually take lambdas as the body. You see, this looks like a C++ lambda as the body.
Yeah.
So that's actually a library function built on lower level
So
things.
the pipeline last is not a primitive, it's an actual Kanagawa function.
Yes, and one thing that we do, and we're going to keep doing,